Okay. Check the monitor up there. Okay. And there we go. Good morning. This is Jim Heisey at the Collegiate Space Mining Challenge, hosted by the Cardinal Space Mining Club at Iowa State University, coming to you from Ames, Iowa, and the Student Innovation Center on the ISU campus. I have here with me Cole Grainer with the University of North Dakota team. They're going to be the first team up this morning. And so before the robot's ready to go, I thought I'd take a few minutes to grill Cole about his robot. I want to learn all their secrets in their design. Never know when we might be able to use something in ours. No, just kidding.
Of course, yeah.
But also a lot about your team too, and how many you have in your team, and you've got a fair sizable group here looking down through the list of names. So
Yeah,
thank you for bringing them all along and coming here to the middle of Iowa
of
for
course.
our little competition. And so tell me about your robot.
Yeah, so our robot is a sort of a tank drive four-wheel robot. It has a bucket ladder system,
Okay.
which allows us for a very compact, very short total overall length because
Mm-hmm.
it's a very vertical ladder system. It has about a 60-degree change in direction at the top.
Okay.
uh, and that allows us to kind of like, once I said again, shorten it all up, but it also is a rear dumping hopper.
Okay.
It is a big difference from our last year's design. Last year we had what a lot of people call belly dumps,
Okay.
but we had one big issue is we would end up turtling ourselves, is what we called it,
Yeah.
where we would dump too much regolith at once, and all that regolith would kind of pile up right on its belly, and it would end up losing traction.
Now it's sitting here just
Oh,
kind of not going anywhere else, trying to get off the pile of dirt. Yeah.
yep, like
Yeah.
a little turtle with too much sand on its belly.
Oh, how cute.
Yeah. Yeah, no, but our robot's name is Susie.
Susie. Okay.
It is kind of in light to our old mascot. I believe
Okay.
back in 2017 or so, we changed from the Fighting Sioux to the Fighting Hawks.
Ah,
A lot of people didn't like that. I'm sure it's very similar to not Fargo, Florida, where they
yeah.
had the
Seminoles.
Seminoles. Very same concept.
Yeah.
They wanted to just kind of change the logo, rebrand it. So yeah, our robot is kind of in respect to our old our alma mater's mascot.
Heritage. I like it. I
Yeah.
like it much. How much does your robot weigh?
Our robot weighs 47 kilograms, which actually surprised us as well today because
Uh-huh.
last time we measured it was at 49 kilograms.
Ah.
One big factor that resulted in having our lower weight is our wheels.
Oh,
Um,
okay.
Pretty proud of them. We put this is our third iteration of them actually. Is it moving? No. No.
No, not yet.
Third iteration of them, and
We still have about 5 minutes left on the setup time. So,
beautiful. Yeah. Yeah, our wheels, I can confidently say we have the lightest wheels in the competition today.
okay.
I believe they're all about 600 milligrams.
Wow.
For the American listeners out there, I believe that clocks are around 1.5 pounds, a little bit less,
Yeah, a little bit less than that.
somewhere in there.
Yeah. For
It
four wheels.
all per wheel,
Oh, per
per
wheel.
wheel, per
Okay,
wheel.
that's still
I
very
believe.
light. What are they made out of?
Yeah, so we have it is started out with a PETG 3D print
Okay.
of the rim itself.
Mm-hmm.
Then we have it all wrapped in carbon fiber. It's all continuous as well. It definitely does add the strength quite substantially as compared to its weight. But we also have our rims are made out of 5051 aluminum.
Okay.
The reason it's 5051 is simply because of our sponsor,
Mm-hmm.
PS Industries. It's I believe they're more local to Grand Forks. They use a lot of 5051 for its ease of machinability and corrosive resistance. Um,
Interesting. Yeah, I was just recording a lecture for my manufacturing engineering class this morning and was talking about uh, modulus of elasticity, modulus of resilience, and strength. and how a lot of teams, when you're engineering things at this point for competition, they love to use 6061 T6. Yes, you can get a hold of it, but the thing you got to keep in mind is that 6061 T6 does not like to be welded, does not like to be bent, it does not like to be machined.
Yeah.
So what is it good for? Well, only for strength. But what we need to keep in mind as engineers, and as you're well aware of, stiffness. And because it's really about deflection and how much do things move. And there's no gain between 5051 going to 6061 T6 on stiffness. So it's something to keep in mind. So what is the drive connection between the wheels and the drivetrain itself, the motors? Is that spline, key, hex? What are you using?
Yeah, it is a round shaft with a key. It's a
With a
keyed
key?
shaft.
Okay.
Has been very it has definitely added to the challenge of the design phase.
Okay.
Looking back, if we were to go back, we definitely would go with hex shafts.
Okay.
That's what our previous teams have used. But we kind of went on our electrical engineers. We gave them the full freedom to pick the motors, the gear train,
Yep.
the gearboxes, and everything all the way out to the wheels. And their decisions led to our round shaft with key, and we had that challenge to design around it, and I'm proud to say that we hopefully have met that challenge.
Excellent.
They are flip ski motors, flip sky.
Okay.
They're rated for 140 kV, so more on the keeping high efficiency when they're rolling at the high RPMs. I'm kind of showing my my electrical engineering
Yes,
skills.
yes,
Yeah.
yes,
No,
there you go.
I'm definitely mechanical.
Yeah. How many watts does that motor put out?
How many watts? That's an
Yeah.
excellent question. I don't know the number off the top of my head.
Because the kV gives us an idea how fast the
How
motor
fast.
run, but it doesn't tell us the total power
Okay.
on that. Kind of interesting. What voltage are you running on your robotic system?
Yep, it's a dual voltage 2412.
2412.
Yep.
Okay.
And yeah, it is. It has. We also run on Jetson for a computer, which has also proved to have its own challenges as well.
Ah.
Because the GPIOs, the general purpose input-output pins, have not been responding in these past 4 or 5 days we've been working on it. Which,
Okay, for us that have no idea what you just said, what does that mean in layman's terms?
essentially, we have two motors that we want to run, but the computer is not figuring out how to send out a signal to it.
Okay. Yeah.
And that would be our hopper door and our offset motor to vibrate the hopper.
Okay.
So our entire robot strategy is to, like I said, like that hopper, or not the hopper, the bucket ladder system. We'll get the regolith to the hopper, and the hopper itself is about a 35-degree angle, which is not quite enough on its own for the regolith to just kind of slide out.
Yeah.
Because it has that very high angle of repose.
Right.
It likes to clump up when it's stationary, but once you get it, can I shift this around a little
Oh,
bit?
yes, go right ahead.
Actually,
But hold that
probably.
up where people can see it and make sure they can see the clear side of it. So you can kind of see the material in here. And what he means by angular repose is he turns this when it starts to move. And this material's been sitting there, so it's a little compact. But you see now it's starting to move. If that were sand, it ought to be to the lid of the container. But the lunar regolith that we work with in here, depending on whether it's in loose state or the compacted state, will tend to just want to stay put. It does not want to move until you put vibration into it, and then it goes everywhere.
Starts acting a little bit more like a fluid if that
Yes.
picks up.
Yeah, I think it does, but it's hard to see because of latency in the computer screen. We just lost our feed for what we're talking here. The robot's running good. We're more interested in that. So it looks like we're on the start of our competition run. So very interesting looking wheels. I'm gonna have to go down the pits and take a picture.
Yeah.
Yeah. Well, I've got the feed to the pits. We're not seeing us, but that doesn't matter.
Yeah. Yep.
Okay. Yeah, we have a lot of fun here. This is the first time we're doing this competition for folks online, so we are learning as we go to be TV personalities, so to speak. It's not our first profession. It's not our day job. Our day job is being engineers.
Mm-hmm.
And Cole here is with the University of North Dakota, electrical engineer, I take it?
Mechanical.
Oh, you're
Mechanical.
mechanical. Okay.
Yes, I was trying to find all the right electrical engineering
Sure.
words over there,
Okay.
but yeah.
Ah, okay. Yeah, I try to do a lot of electrical work too, being a mechanical. But yeah, so now here's another good question. You said it was flip sky motors. What are you using for motor controllers?
Motor controls, those are O drives.
O drives?
And we
Okay.
have a separate electrical box just for those O drives, and we got
Hmm.
another electrical box for all of our other kind of like uh, lower heat components.
Okay. And what are you running for batteries?
Batteries, we have 3 batteries in parallel, lithium ion batteries, I believe.
Lithium ion.
I
Okay.
believe. And yeah, I
Okay.
they have enough power to run for about 2 hours on end. We did a little bit of testing last night, and we ran them for about 25 minutes to half an hour, and we only lost about zero point 0.2 volts total.
Wow.
We definitely overshot our need for the batteries.
Yeah.
Um,
How much battery weight are you carrying on the robot?
the batteries total, we have like so we designed our battery box to just be able to drop out with a couple pins,
Nice.
and we weighed that. I believe we weighed that on the pound side, not the kilogram side.
Hmm.
It was roughly 7 pounds, 7.5 pounds total for
Okay.
the whole
So
battery
we're
box.
looking about 3 kilograms of weight
About three
for the
kilograms.
batteries. Not bad. Not bad. I thought it would be a lot more being the lithium ion batteries, but that's really pretty decent. And given the energy density that you get out of a lithium ion battery as compared to, say, a lead acid battery or a lead gel acid battery, which are very heavy and not have a lot of power capacity, or a lot of the other teams, including Cardinal Space Mining, we use lithium polymer batteries. Uh, they are excellent power density. You can pull a lot of current off of them. You can get a fairly good runtime out of them, but they take up more volume than your lithium ion. So if you have volume to spare, they're great because they're very lightweight. The big downside on the lithium polymer batteries, if you pull them too hard or pull them down too far, they will catch on fire
Mm.
and they will burn nicely. And lithium ion batteries, yes, they will burn too, but they're a little more gentile than the lithium polymers. And so we've taken safety measures here at Iowa State for all the different types of batteries they have here. So in case we do have a battery fire, we're prepared to deal with it either in the competition arena or in the pit area, because safety is first here at Iowa State. And we're doing a great job so far because we have not seen any battery fires. We have not seen any catastrophic or unplanned disassembly of vehicles, or RUD, as Mr. Elon Musk would call it.
Spontaneous disassembly.
Spontaneous unplanned disassembly, yes. And so the competition has been going pretty well. Our biggest issue has been our own technology with bringing this competition to you as we sort out all of our communications. Somebody ran over one of our internet cords yesterday and it stopped working, and that was causing a lot of our connection problems, which slowed down our runs. I think we have that problem solved today, so hopefully we'll see a lot more teams running here. Right now, we're 5 minutes into North Dakota's run. The robot still has not moved, so we're
Hmm.
still fighting the gremlin problem with getting robots connected. I may have to get out my patented gremlin traps here later today. I brought them with me to Florida one year, down to the Kennedy Space Center after we had had a year with so many technical problems. And we put those up. They look like fly traps, but they're
Oh,
very, very
there you
special
go. And yeah,
because what we have is there's a little mechanical trinket at the bottom of each fly trap, because that's what gremlins go for, is anything mechanical or electrical. So if you entice them just like cheese in a mouse trap,
mhm,
you can catch those buggers and we can stop these sort of problems.
exactly.
So as I was telling all the teams when we had the gremlin traps out, it's not a technical issue or a design issue. It's a gremlin issue. And if we can get all the gremlins trapped, then things will run very well.
Yeah,
So maybe I'll have to get that out
yeah.
today, later today, and we'll get that in place, and then maybe we'll be able to get everything running even smoother than what we have. For those that are listening online, uh, the results from yesterday that we had for the teams that did run, the San Diego State University. And first, I'm going to say an apology to the San Diego State team, their fans, and the parents that were watching yesterday, because I did a Freudian slip yesterday and several times called them South Dakota State University. I'm very sorry about that. I have a good friend at South Dakota State University, and I just for some reason said that when I saw SDSU. But San Diego State, Team Creed, did the best run yesterday. They garnered 852 points out of their run, followed by New Mexico Tech, the minor 49ers, got 767 points. Our rookie in the competition here, what I mean by that is this is their first year doing anything with NASA Lunabotic style space mining. They had a run point total of 428 with their little robot that made things look very routine, what they were doing. Our University of Arkansas Razorbots, they scored 262 points in their run before things stopped running on their robot. And Iowa State Cardinal Space Mining Club, who is not competing, but we are demonstrating in the run, so we're keeping track of how we do in here too, because we're always in search of more data. We did 222 points in our run. We had an issue in that our actuators wouldn't actuate for raising and lowering our bucket ladder. And so they did what I call the Billy Preston maneuver, and they kept running the robot in circles to create a big enough mound so they could dig up some regolith and then dump that, since they couldn't get the bucket ladder down to digging depth from driving depth. So very, very interesting maneuver by our team to get that done. It looks like they're pulling the robot. They called it because it couldn't get a connection. So unfortunately, it looks like a scratch on this first run. I know you'll get a chance to sort this out. We'll have it back for another run. And it looks like we'll have a quicker setup between runs because we don't have to reset the arena.
Fair enough.
On that. Well, Cole, thank you.
Yeah, thanks for letting me out
sitting
here.
in. I look forward to getting you back here on the next run. I wish you the best of luck at getting the gremlins taken care of. I'll go see if I can go find my gremlin traps.
We'll go hunting. Go hunting.
All right.
Thanks
care.
again.
Thank you. And thank you for being here at the CoSMiC competition. We really appreciate it.
Thanks for the invitation.
Yeah. Okay, well, there you go. Another example of the technical difficulties of running space mining, because it's not just going out and digging up material. You've got a robotic system, but you've got communications that you have to do. Telemetry, you've got programming, and all the other things that go along with designing either a teleop or an autonomous robot. These students spend hours. I'm not talking just 10 hours or 100 hours. One of the teams told me they kept track of their time this year for the 9 months they've been working on it. The team invested a total of 4,500 man hours in designing, building, testing their robot, and getting it ready to come here to this CoSMiC event. And Iowa State's Cardinal Space Mining Club does the same thing. I'm very, very proud of the work that our team puts into their efforts in getting a robot together. And the same is true for all the teams that just finished competition down at Florida for the NASA Lunabotics. The top 10 teams from the UCF portion of the competition that started last week on Friday ran through the weekend, and then the top 10 teams went to NASA and competed there. The first place team in autonomous operations at the competition wound up being Purdue University. So congratulations to the Purdue University team for having a robot that was doing a very good job of driving itself. And first place in construction, which is mining and what we're doing here in CoSMiC, wound up being the University of Illinois at Chicago. So congratulations to that team with their run. They also received the Regolith Mechanics Award for their very unique digging system that uses a very powerful vibrator to actually sink the robot down into the regolith, and then it picks itself up and carries that load, and then uses the same vibrator that got the load to unload the robot by reversing direction. A very unique, very active way to do that. And then finally, the grand prize winner of the NASA Lunabotics 2025 competition was the University of Utah. So congratulations to Utah for a magnificent competition this year. Look forward to seeing them next year. Hopefully Iowa State will get through the cutoff list for next year, or that NASA can expand the field of who they can have there. And we'll get the chance to see all those wonderful teams and their advisors and their students down at Florida next year. During the meantime, the reason we have this competition here is we have 12 teams that because of the restriction in facilities that NASA suddenly found themselves with, or more specifically University of Central Florida, they had to do a restriction as to the amount of teams that they allowed into the competition. So what they had not done in the past is use the project management plan as the first cutoff as for teams that were allowed. And they suddenly did that this year, and we suddenly found ourselves, because of a technical glitch in scoring of the reports, that we and 12 other teams, including 5 of the top 6 teams from last year's competition, not in the competition this year. So I talked to our club, which was very disappointed, asked them to think of something positive they could do. And they thought beyond themselves. They thought about the other teams that didn't have anything and how that impacts their club as well, because we would still want to design, build, and compete a robot. So they said, well, could we run our own competition? I said, certainly. But you're going to have to do it getting help from the university, and they did just that. So my thanks to Iowa State University College of Engineering administration for giving us the green light, and for Hannah Albrecht and the conference planning and management team at Iowa State University for helping us put this competition together. We could not have done it without them. And then, of course, our wonderful sponsors, Caterpillar, Danfoss, Seek, Sensor Systems, Mechdyne, Collins Aerospace, the Iowa Space Grant Consortium, and the Iowa State University College of Engineering. All provide us sponsorship resources to bring this competition to you and our teams that are here as our guests. And so we're very happy to be doing this. You see sitting here in front of me this very interesting thing. This is one of our trophies that we'll be giving to the top 3 teams at the CoSMiC competition. It's very unique because this little glass crystal ball here actually is a laser map of the moon. That little hazy circle you see inside there is a relief of the moon, and then we have the arms here that are water jetted aluminum, and the rest of this is 3D printed plastic, but we have fiber optics going through here, and it runs off a USB drive, and that lights up the orb. It's just magical in a dark room. This was designed for us by one of our own club members, Mason Eck, who designed this and built these trophies. It will sit on a beautiful polished wood pedestal, and with a plaque on it that will denote the CoSMiC event, first, second, or third place finisher in the event, and that will go to the top 3 teams in the competition. All the other teams will be receiving a plaque. They'll also be receiving a nice bottle of our ISU regolith that we have in our lunar test chamber as a token of our appreciation for them being here, and also a little bottle of it to each club member for each team to have to remember this event by. Again, we're located at Iowa State University in Ames, Iowa. This event is coming to you from the Student Innovation Center and Iowa State campus here on the west side of campus amongst all the engineering buildings. My name is Jim Heisey. I'm a distinguished professor of practice in the Department of Mechanical Engineering and the faculty advisor to the Cardinal Space Mining Club. Who do we have up next for NU? Okay. Going down through my Northeastern University, NU Lunabotics is going to be the next team up. About what time do we expect them to run? I'm getting some information from my mission control people over here. What's that? Close to 9 o'clock. Okay, so in about 5 minutes, we'll have the NU team in here ready to run. And I'll get one of their team members up here to talk to us about their team and their robot. And we'll see you then. I'll turn it back over to the people in the box, our arena, as we're calling our arena. And it looks like they got things ready to go. The door's open for the next team to load in. And we'll get our next competition run in here in 5 minutes. Thank you. Perfect. We'll ask you questions about your robot, about your team, and are we coming back live?
It should be.
Yeah, I'm waiting to see that we go live here.
You went to the place you recommended. It was very good.
Which was Hickory Park?
Yeah, Hickory
Hickory
Park.
Park. What'd you have for ice cream?
Oh, I got like a coffee fudge thing.
Oh, how was it?
It was good.
Yeah, I've had those many a time. Too.
Yeah.
Okay, we're back and at the collegiate space mining competition or challenge, I should say. I'm here with Matthew Geisel or Giesel?
Geisel.
Geisel from Northeastern University. Can you tell me where Northeastern University is?
Yeah, we're in Boston, Massachusetts.
Boston.
Yeah.
Ah, okay. I should have caught the accent.
I'm not from there.
You're
from,
all.
Yeah,
No,
I'm from New Jersey.
You're from New Jersey.
Yeah.
Okay, so that's why you're not talking like Boston.
Yeah.
Yeah. Okay. I shouldn't stereotype. Excellent. So, thank you for making the drive here to Iowa. That's a fairly good drive, isn't it?
We actually flew.
You flew.
Being
Okay.
in Boston, not a lot of people on the team have cars.
Ah.
So we just
yeah.
took the robot, packed it in suitcases, and then
Oh, you
brought it on the
packed it
plane.
and brought it on the plane.
yeah.
What about your batteries? What sort of batteries are you using?
We spec'd our batteries to be FAA compliant.
Ah.
So we used really small batteries that were under the 100 watt hour limit.
Okay. And how many of those do you have in
We
the
have
robot? Two?
We're a very light robot.
Very light robot. How much does it weigh?
It weighs like 23 kilograms.
That is light.
Yeah.
The lightest robot I ever seen at a competition was 10 kilograms.
Wow.
I'm trying to remember if that was Alabama or University of New Hampshire. It was one of Alabama's early designs. It didn't collect much, but it had some very good stuff. That was the year Alabama beat us by a half point for the grand prize
Ooh.
in 2013. Or no, 2012. 2012. We won the mining. Our robot weighed 41 kilograms that year, but we collected a lot of material.
Yeah.
Their robot weighed, I think, 12 kilograms or something like that, but it collected like 10 kilograms of material. But being so light and then having a lot of autonomy points built into it, they beat us by a half point with
yeah.
their performance and other things. So Iowa State and University of Alabama go a long ways back for being competitive in this. So tell me, you've got a sizable team here along with your faculty advisor. How many members are in your team?
So the whole team is about 15.
Okay.
This is our first year. So
Oh, a rookie too.
yeah.
Okay.
So this is our first year competing. We started from basically nothing in the fall
Uh-huh.
and then built up from the ground up, and now we're at 15.
Okay, 15 members, and pretty much got all of them here
Yeah, we have a
practically.
lot of them here.
Yeah, well, that's excellent. That's excellent. Now, is this a club or is it a senior design class?
Yeah, this is a club. So at Northeastern, we have we're umbrella club called SEDS, Students for the Exploration and Development of Space. And so
Okay.
we just decided to start a new project team this year to work on the Lunabotics project because we thought it was a really interesting challenge.
It has been. It's been going on for some time. Iowa State's been involved with it since year one
Wow.
of that competition, and it's been an excellent training ground for our students in learning robotics. So, tell me about your robot. What is its system features in the
Yeah.
robot?
So we utilized a lot of 3D printed parts for
Okay.
our first competition because we had access to 3D printers and it was easy to rapidly prototype. We use something called a rocker chassis system,
Okay.
which is the wheels are on two rocking, basically little triangles without the bottom part. So, and
Okay.
those rock independently of each other. And then in the back, we have something called a differential bar,
Okay.
which holds them in place. So if
So
one goes up,
very
the other
much
goes down.
like the suspension system that's used on Curiosity or
Yes.
Perseverance.
The reason we took inspiration from our SEDS has a Mars rover team that does
Okay.
a different project. So we
Which
took
project is that?
This is a competition where they compete in Utah.
Yeah, that would
with
be
other
Maverick,
Mars.
I think, wouldn't it? Or
I don't remember then. It's
Yeah.
the University Rover Competition, URC.
URC? Yes.
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 So we took inspiration from that. but we were trying to build a small and light robot.
Yep.
So instead of a 3-wheel system, we're going with a 2-wheel system on each side.
On each side. Okay. Excellent. What's your material collection and deposition systems that you're using?
Yeah, so we have for our material collection system, we're using 2 chains with what are called K-links, which are basically special chain links that kind of fold out.
Mm-hmm.
And then we have 3D printed scoops that run along that chain.
Okay.
And that chain is on aluminum tubing frames on each side, which
so,
have standoffs to keep the chain in
the
place.
general parlance we've used in the competition for a lot of those are called bucket ladders. If it's
Bucket ladders?
bucket ladders, as they go. We'll have to forgive him because he's a rookie on this, so we'll get him up on all the terms of the competition over the years. So that I assume would be emptying into a hopper
Yes.
or some sort of box.
Yeah,
on
it
the
empties
robot?
into a hopper. We're using aluminum frame with acrylic paneling.
Okay.
We're probably going to switch from acrylic because we had some issues with transporting it on the flight.
Yeah.
But the hopper is fine.
Yeah.
And then that has a little trap door at the bottom that we're using for
So you're
deposition.
dropping it right out the bottom
Yeah.
of the robot.
Yes.
Okay. Very good. Very good. Very interesting. It'd be fun to watch that robot run. And so it's running on lithium ion batteries.
It's actually running on lithium iron PO4 batteries, which are a slightly different type of battery.
Okay.
Which we chose. They're a little heavier, but they're a little safer.
Yeah.
So we chose them so we wouldn't have any battery fires, and because we're a new team, so we didn't want to have to worry about dealing with too much discharge on the battery.
That's very wise. It's usually good to manage your risk, so
Yeah.
to speak, in doing a robot, and especially if you're going to carry it on an airplane, and you don't want the cabin crew to be very unhappy with you if you have an issue with a battery on board an airplane.
Yeah.
People tend to frown on that sort of thing, you know. Okay, so your team, 15 students. What sort of majors make up your team?
Yeah, so we have a bunch of engineering majors like all over the disciplines. We have probably like 4 or 5 mechanical engineering majors, 3 or 4 electrical, and then a couple of software people who are
gotta have
computer
them.
science and computer engineering,
Yeah.
those sort of fields. We found when we came here that a lot of the other teams are very mechanically focused.
Yes.
So we're hoping that we can this year, hopefully, but next year, additionally, step into the autonomous field
Yeah.
more.
Well, that's the whole point. You get involved with these things, you come to the competition, you look at everything that's going on with the various different teams, and you learn.
Yeah.
And then you go back and you do more, and that expands your knowledge of what you're doing with things. And that's the whole reason for holding these competitions, is to allow students like Matthew here to really expand their education and turn them into much better engineers than they would be without that. This is why the hands-on education part of doing these competitions is so vital to the education of our future generations of engineers and team managers and the like. So, and that's one of the key reasons why we chose to host this competition here at Iowa State University. So anyway, we're waiting for the NU robot to get into the arena. Yes. Okay. All right. I just got word that your team is having connection issues again. And is it on our end or their end? Oh, well, this is a rookie team, so we'll have to forgive them for that. Okay. They are missing a very vital component that we thought we had told every team to bring in. It's called a router. And you can't get connected to the Wi-Fi without a router. And so we may be doing a quick practice run because we're finding them a router. And not to be confused with the carpenter tool that I love to use a lot for shaping wood. This is a computer router that allows you to use Wi-Fi to connect between the robot and the internet line that we're using to run the robots. So So at any rate, we'll come back to you guys after you get a chance to do your practice run on this, and we're going to get you scheduled for a later time.
Okay.
So Matthew, I thank you for your
Thank
time
you.
on this, and good luck.
Thank you.
And we'll get you on another run here at CoSMiC.
Thank you.
Okay. And I saw Hannah Albrecht running around here in the room a minute ago. I'd like to get her over here if I could. That's the CPM personnel. So we were hopeful that we would have all our run issues kind of sorted out this morning, but as you're seeing, not everything works as planned. And so as engineers, we'll just do what we need to do and work through this. And during the meantime, I will continue to share information as best I can as we go through this second day of the competition for the Collegiate Space Mining Challenge at Iowa State University, hosted by the Cardinal Space Mining Club at Iowa State University. This is the first time doing this competition. We have been an active club since 2009. We typically have between 40 and 50 students involved in the club, and generally we'll take a team of 16 students to competition and down to the Kennedy Space Center to compete in the NASA Lunabotics Engineering Challenge down there. The focus on the challenge is, as we've been saying through yesterday, and you'll hear this a lot today, is space mining. But in this case, rather than mining for gold or mining for silver or things like that, really our key focus is mining on resources that the astronauts will need to survive for a long-term stay on the surface of the moon or Mars. And so that's going to involve rocket fuel, it's going to involve building materials, it's going to involve, most importantly, water. And both the moon and Mars do have water in their surfaces, but we have to dig below the surface to get to it. The other key thing that we can get a lot of off the surface of the moon is oxygen, because moon is 45% mass oxygen, but it's in the form of oxides. Metal oxides are very prevalent on the surface of the moon because of the bombardment of the solar wind. Since the moon has no atmosphere on it, oxides form very readily on the surface of the moon. And those can be mined up and processed, separated from the metals, and then we have oxygen to breathe for the astronauts, or oxygen to use along with the methane that we can find on the moon to create low-grade rocket fuel for blasting off the surface of the moon and doing exploration at other parts of the galaxy and the universe and the solar system, of course. The key thing here, why the moon? Well, it makes an excellent jump-off point for deep space exploration, because gravity is our biggest issue, and it takes more rocket fuel to get off the surface of the Earth to go explore space than it does to get off the surface of the moon. To give you an idea, I was talking to yesterday, if you want to get a kilogram of cargo off the surface of the Earth into low Earth orbit, it's going to take you probably 500 kilograms of rocket fuel just to do that. If you want to get to high Earth orbit, it's going to take you another 4 kilograms per kilogram of what you had to have to get up there to get to high Earth orbit. And then past that, you need another 2 kilograms to get to the moon. So by the time you've got that all said and done, because you take 1 times 2 times 4, you got 8 times 500, and next thing you know, you got 4,000 kilograms of rocket fuel that you have to have in your rocket just to get that 1 kilogram of cargo up to the moon. And that's why the Saturn V rocket was so big, why the SpaceX Starship is so big, and why the SLS rocket that NASA hopes to fly to the moon and do deep space exploration is so large as well. It takes a lot of rocket fuel to get out of what's called the gravity well of Earth. Now, if you try to do that from the moon, the gravity of the moon is 1/16 of the Earth, And so it takes a lot less rocket fuel to get off the moon and to go into places where we want to go explore. If you use an asteroid, then it's even less, because the interesting thing in doing space mining is that in order to dig material, you got to have force. In order to have force, you got to have mass. In order to have mass, you got to have gravity. And you can kind of see how this all compounds on it, that what we have to work with as engineers. A big part of what we have to look at here in designing these systems is understanding the relationship between the downforce that we have of the robot given its mass and the sort of side forces we have to generate in order to cleave material and get collected into scoops. So a lot of time what we spend in doing engineering is understanding what is the direction of our forces, how do they combine with each other, and is that going to allow that robot to stay in place on the surface, or is it going to tip over? Or in the case of an asteroid, which has what we call microgravity, it's not a 16th of the Earth's gravity, it's more like 1/1600th of the Earth's gravity. And to give an example, what is that like? Well, if I take an astronaut with a shovel and he takes that shovel and points it into the asteroid and then stomps on it to dig a hole, he has just achieved exit velocity and will never come back to that asteroid again. So these are some of the challenges in space that we have to deal with in going and doing space mining. So we got to understand the size of the body we're mining on, what sort of gravity we have to work with, what sort of digging are we going to do, and then engineer appropriately. In the case of this year's NASA Lunabotics Engineering Challenge, we're now focused less on collecting water, because we've done a lot of that for the last 15 years. And we're now want to be thinking about, well, how do we prepare a moon base and have that ready to receive astronauts? And one of the big issues there is a rocket, when it lands on the surface of the moon, kicks up a lot of dust at very high velocity. We're talking about thousands of miles per hour or 1,000 kilometers per hour velocities close to the launch pad. And this material, giving no atmosphere, will travel long, long ways and can cause a significant amount of damage to any structures that are close by. Well, we don't want to drive 20 miles to get from the launch pad to our shelter, or from the shelter to the launch pad. So what we need to do is we need to build a protective enclosure around the launch pad, and that's called a berm. And it's a big pile of material that acts like a protective fence around the launch pad. So as a rocket lands, and this is a material, or ejecta as we call it, that gets blown sideways toward our moon base, is going to hit this berm and it's going to get deflected upwards, and it's going to kill the velocity on that ejecta, and it'll fall down vertically harmless or over our moon base and not damage it. And so that's the objective here, is to build a berm and have a protective environment for a space camp. And so that's what we're doing here. We're training robots to construct, and that's what NASA called that part of their award this year, was the construction award with doing space mining. So I'm going to get more information from our crew here and find out what's happening next and who we have coming up. And I see you're playing some video online. Never mind. So who do we have coming up next? MU? NU. Okay, they're still trying to get their test run going. Okay, well, I'm going to go ahead and sign off for a little bit. We will come back with you soon as we get more information what's going on. This is the Collegiate Space Mining Challenge at Iowa State University. Thank you. So they'll get me camera feed here in a second.
Sounds good, Jim.
Yeah. This has been a fun adventure.
It's been
Okay.
cool.
Yeah, it's been great. Well, I want to welcome you back. If you've been watching, Northeastern University out of Boston, Massachusetts, testing their robot. They are a rookie team. This is their first time they've been doing any space mining like this, and so we've been very flexible here because what we really want to do is we want the teams to be able to learn at this competition. It's not about can you win, it's more about what can you learn, and so that's been our key focus at this competition. But I want to take a minute here and talk with a very dear person to me who has helped us make this competition a reality, and that is Miss Hannah Albrecht of Conference Planning and Management at Iowa State University. If we didn't have her help, this never would have happened. So Hannah, thank you
Of course.
for your help in all this. So tell me a little bit about your organization and what you do here at Iowa State.
Sure. So our office, as you said, is Conference Planning and Management. We plan between 110 to 130 events every single year, ranging in sizes of 15 people for an all-day visit to events all across the country. We've done events in Texas, New Mexico,
Wow.
Missouri, Iowa, just in the past year. We're unique to Iowa State in the fact that, we get hired out by non-Iowa State entities. So we can do events not just for student organizations, offices on campus, but also non-Iowa State groups as well.
Excellent. Do you do anything with athletics as well?
Not necessarily athletics, but for example, right now we have Special Olympics going on. They're using athletics facilities, and
Yep.
so we're connected with them. We host events at Hilton, Suco Benzone, Schumann Building all the time. So
Aside from this event, what is the most unusual event you've had to help out with?
most unusual. I
Yeah.
mean, this one takes the cake absolutely for probably making. I call this my resume builder. This one has made me
excellent.
learn a lot. But after this one, I would say I planned an event that went to the National Balloon Festival in Indianola, and they had a VIP suite and catering.
Oh, very cool.
So transportation for that, getting everyone there, get their tickets, and how do you do a VIP suite at a balloon festival in the middle of a field?
Oh yeah, Hallmark Movies just did a
Yeah.
movie with balloons. I was thinking, gee, we could get them to Indianola and do a movie there too.
There you go.
My wife watches Hallmark all the time, so she doesn't like watching the news, so that's her stress reliever. Well, great. Well, so it's been a little unusual then working with a group of engineers like this that are, you could say, moon crazy.
Just a little bit, but
Yeah.
we've come up with some good moon dust jokes along the way as well in our office.
Oh, please share.
Well, for one, if you didn't know, in the Student Innovation Center, you can't actually tape anything to the walls sign-wise, but you can bring moon dust in.
That's true. Yeah, for those that are watching, we have a lunar test chamber in the basement of the Student Innovation Center that we have this material, the ISU-1 in. It's a combination of Portland cement, coal fly ash, and fine sand, and it behaves both mechanically and electronically, and the reason why I say that, this stuff will pick up a static charge very easily, and it's very abrasive, and we actually have this stuff stuck to the walls in our lunar chamber 6 feet up off the floor, and it's stayed there for now years that we've had it in there, and we can brush it off, and then we go run some more tests, and it winds up on the wall again. And this is just the sort of thing that the Apollo astronauts had to deal with. It would stick to their suits, and they drag it into the spacecraft with them, and then it would start floating around the spacecraft, and they'd breathe it in.
Oh, wow.
And at the end of all of the Apollo missions, the astronauts would come back with a coughing issue because of all of the
Particles.
silica dust in their lungs that came off of their spacesuits that
Interesting.
collected because it's static. As they shuffle along, it's just like walking in the carpet. You've done
Oh,
this where
yeah.
you walk in a dry carpet in the middle of the wintertime and you touch a metal object
Oh,
and you
yeah.
get same thing on the moon. So very, very interesting. So, but no, we want to thank you so much for helping us make this event possible. Hoping maybe we can do it in future years, but I don't want the club to be doing it. So
Yeah.
I'm going to put a shout out there to the other student organizations at Iowa State University that maybe want to get the experience of planning an event like this to build your resume, as
Yes.
Hannah said, because this would be a wonderful opportunity for you to help us and to help other teams. Like I have the University of Minnesota sitting here waiting for their robot to run next, to have that opportunity to learn,
Absolutely.
to practice, and to compete.
And I would say, we've got it figured out now. Now we just got to plan it again.
Yeah, we've got the first thing worked out. The next time it'll be easier, right?
Whole lot easier.
Yeah.
I think
so.
EH&S would agree with us as well.
Yes, they would. Now that we know what to expect, I think the next event will go much better. So Hannah, thank you so much.
Of course. Thanks for
Really
including
appreciate
us
the
as
time.
well.
Yes, absolutely. It's all a team effort, right?
I would agree.
Yes.
It's been
Okay.
great to work with you.
Okay, that was Hannah Albrecht with Iowa State University Conference Planning and Management, who has helped us set up this collegiate space mining competition or challenge here at Iowa State University. Thank you, Hannah.
Thanks, Jim.
Okay. All right, so we are getting the arena set up. Northeastern University from Boston, Massachusetts just had a chance to test their robot. They were having some issues. They're a rookie team, which means they have not even been at the NASA competition in Florida. So we're really very excited to have them here, to have the opportunity to design, build, test, and learn, because that's how we make better engineers, and that's how we find new discoveries and on different ways to do things in doing space mining. I think next up is going to be the University of Minnesota when they get their robot in there, and hopefully I'll be able to get one of their team members up here to talk with me and learn more about their team and their robot, and then we'll hopefully get to see another competition run here. The technical challenges and communication, we got things worked out from our end, but now we're finding that a lot of the teams have, because of the equipment that they brought, doesn't want to work with our equipment, and that's always a technical challenge. As you probably well know, computer systems are changing all the time, router types, and will they talk with each other, and that's always a challenge. So as we learn more about which sort of systems to tell people to bring so that we have better reliability, we have to deal with these sorts of issues and just work them as they occur. So right now, our team in the box, as I've been wanting to call it, our lunar simulation chamber, or getting the surfaces worked loose. This is the material in here behaves very similar to the surface of the moon. It's a crushed lime rock. The main difference, though, is it does compact down faster than what lunar material does. And so we want to make sure we got it worked loose so that the teams going in here mining have the same sort of surface to work with each run. So they're going through smoothing out the divots that the prior robot left, getting the material back into the construction area, and then from there we get the next team in here to run. So looks like we're set up to get the robot in there and do our 10-minute setup run for getting the robot. Right now our team members in there. Who do we have in the box today, this morning? Do we know? Okay, our club members Walter and Jesus are in there, and if I go through, so that'd be Walter Goodsey, and if I find Jesus here, Jesus Soto is our two members in there. So hats off to these guys. They do a very important job for us working in that arena. It is challenging from the standpoint, the suits they have on that protect them from the irritant that the ag crushed lime can be, because it can be a skin irritant. So they have to wear these full body suits. They do not breathe, so you sweat like mad in these suits as you're working in there. Fortunately, it's a reasonably cool day out, so they don't get too hot working in there, but they also have to wear the PPE equipment, as you see, the booties and the latex gloves, and they have to wear safety goggles and M95 masks that they have on, and they have to keep that on while they're working in the arena. When they step out, they can unzip the suit, take the mask off, breathe, try to dry out a little bit. But it is a character building experience for sure as they're working in the arena. So now that they have the berm building box indicated here, that's where the team that's going to be running in here has to drop their material to build a berm. And then the LiDAR will measure that volume. And the team that can build the biggest berm inside that box will be the winner of the mining competition. But also then includes to that is the weight of their machine and their dust-free operation that they have, and some other factors that go into the total score on the competition. The team that does score the best overall for the various different aspects we have in this competition will win a trophy very similar to this one that we'll be giving away to the top 3 teams. The rest of the teams will be getting a plaque along with a larger tube of our ISU regolith, so they could take that home with them and test that. If they want to build a regolith test chamber, then they can use that as a reference point for building their lunar test pit. And every member of each team is going to be getting a little vial like this one that also has some of our ISU1 material on it. And as I'm holding this up here, and it's probably hard to see because of the distance of the camera, but one of the interesting things about moon soil is when you compact it, sand will always flow. And some teams test in sand, and when their robot runs well, they think they're ready to go. But that's not necessarily the case, because moon dust does not like to flow if it's compacted. And I've got this thing turned totally sideways, and if I don't shake it, it's hanging there. And that's called bridging. And material, if it gets wedged in your robot and it bridges, you can't get it out until you vibrate it. And as soon as you vibrate it, then it goes. And so we've had some that have fallen off here, but if I got to tilt it way up here and this little cylinder here won't let it go until I get it vertical, and even then it's not going. And this is some of the challenges we have with this material, because it'll get stuck. You see it's hanging up there in there, and it's falling out in little pieces as gravity take hold. But if you're on the moon and that's compacted, it's probably not coming down. And so now when I shake it, I can get the rest of it to come down. The other interesting thing is the fluffiness of it, and that is how much volume it takes up when it's loose versus compacted. I've got a tub here of NASA's material. It very much, as you can see, it looks very similar to this. I've got 2 lines here on this, and I've got the Minnesota group in here. This is the fully compacted line, and at this level of compaction, it feels like the concrete right there when you stand on it. You still make your Buzz Aldrin footprint, but it's very shallow. If I shake this up heavily and loosen it all up, and it clouds up, after I get done loosening it all up, and I bring it back here, you see all of a sudden I've got a lot more. I didn't add any material in here, but it's now up to here at this point, and the full loose. See, I shook it a little bit, so it compacted very quickly, but fully loose, it's here. And if you step into that material in the fully loose state, it's like stepping in mud. It feels the same way, but it's bone dry. And when you go to step out of it, this actually happened to me one time. They were working in the arena. I stepped in to check how they were coming along with working, and I sunk in 4 inches. And when I pulled my foot out, there was my sock, but my shoe was still buried in the regolith. So I know kids certainly have experience with stepping in the mud and losing their shoe, but lunar dust can behave the same way. And these are some of the challenges that the NASA engineers were running into. They had no idea what they're going to be experiencing on the moon the first time they landed. So that was a real challenge. You know, they had to teach the astronauts how to walk in 1/16 gravity. They found hopping actually was easier to get around than walking. If they tried to walk, they would tend to fall over more easily. So they developed a hopping motion, which you can see in a lot of the videos as they were moving around. It would be very easy to jump 6 feet into the air on the moon, but then you have the issue of rotation and stability. So there are little hops that wouldn't even get you an inch off the ground here on the Earth we get them up 2-3 feet in the air. One of my favorite pictures is Alan Shepard saluting the American flag after he planted it on the surface of the moon. But if you look at the photograph, you'll discover that his shadow shows him 3 feet off the surface of the moon while he's saluting. And it's a pretty cool picture. We're still waiting for the University of Minnesota's team to get through tech inspection. As soon as their robot gets through that, gets in the arena, I'll get one of their team members down here to talk to me, and we'll learn more about their team and their robot. This is the Collegiate Space Mining Competition or Challenge at Iowa State University, hosted by Cardinal Space Mining Club, coming to you from the Student Innovation Center at Iowa State University. My name is Jim Heisey. I'm a professor of practice in the Department of Mechanical Engineering, and I am the faculty advisor for Cardinal Space Mining Club. We've been doing this, been a part of the NASA competition since 2010. We have actually won the competition 3 times in the history of our club, in 2013 and again in 2023. And then we were co-champions with the University of Alabama last year at the competition. The reason we're not there this year was due to a technical glitch and a logistical issue that NASA and the University of Central Florida ran into. They lost their facility. They were going to do their initial pits for the teams to run in to house 50 teams, and all of a sudden they found they only had 37 slots. So they had to narrow the field down, and the teams that are here, amongst many of the teams that didn't get in because of that narrowing down of the field. And interestingly enough, 5 of the top 6 teams from last year's NASA competition did not get into this year's competition. So they are now here at Iowa State doing the mining adventure here in our lunar arena that we have built, which I have called the box, because it's a tight little confined space. It's not little, it's actually 16 feet by 18 feet, and it has 22 tons of crushed lime rock in it, which is about the same density as the lunar material that we would typically use. Our lunar test chamber, which we decided to not use for this competition, has 7 tons of material, and it's just too tight to do a competition like this. So our students sat down, and using SolidWorks, they designed a temporary shelter that they could build in the Student Innovation Center in their outdoor storage facility. And you can see that here on the cameras. It is also it has plastic on it, and it has a HEPA filtration system on it to keep dust from being expelled outside, and it uses negative pressure to keep the dust inside the chamber. We have 2 industrial exhaust fans that are blowing constantly in there, and we have filtration in the ceiling of the arena so that we are continually pulling in clean, fresh air into the arena while they work in there. And since this is not Florida, and it's not overly humid, and it's not overly hot, our conditions are a little nicer in the arena than what we would typically see down in Florida. Though their new arena they now have in Florida in the Student Education Center is air conditioned, and that helps out quite a bit. We have about a 12 to 15 inches deep of material in there. The objective for the teams are to, once they get communication established with mission control through Wi-Fi links, then they are to drive their robot from the start area, which is what the camera view that you see in the upper right corner of your screen. That's the start area that the robot will move from, and they'll drive out of that around the rock wall that you can see in the lower left screen, and then into the construction area that's in the lower right screen, where they will dig up material and transport that to the berm building box, which is that glue chalk line that you see in the lower left screen. They have 2 rocks in there that, if they're capable of moving rocks, they can use that to help build the berm. Otherwise, they have to work around those or move them out of the way if they so desire to do that in order to gain full access into their construction area. So the idea here, as I mentioned, is to build a berm. The higher the berm, the better, but it has to be deposited within that size box there, or they don't get points for it. The whole idea, of course, is to protect a moon habitat from rocket blasts when a supply rocket comes and lands on the surface of the moon. to bring all the vital supplies that the astronauts would need for operating on the moon. However, preferable would be to do what NASA calls in situ resource utilization. That's a fancy word for meaning living off the land. So what sort of things would the astronauts find on the moon? Well, first and most important, water. But where will they get it? Well, they'd have to dig fairly deep under the surface of the moon to find it in areas that can remain reasonably cool. So probably not find it at the equator of the moon because that stays too hot. But at the poles of the moon, they a number of years back did a mission where they called it NASA bombed the moon, and they sent a projectile down into a crater in the south pole of the moon. And then the spacecraft itself followed the projectile down so it could fly through the plume of dust that the projectile raised when it hit the surface of the moon, and sent that data back before it too crashed into the surface of the moon. What they found when they crashed into the bottom of that PSR, as they called it, which stands for permanently shadowed region on the pole of the moon, they found enough water density out of the material that was disturbed to fill 20 jugs of water, like what you'd have at a water cooler. So there's a lot of water on the moon that is in the form of cryogenic ice in those extreme areas. So that's great. We got water on the moon. We can go get it. Here's the engineering challenge. Those permanently shadowed regions have a temperature of about 40 degrees above absolute zero. What does that mean? Well, it's an engineering term. Absolute zero is so much cold that all atomic action stops. Electrons stop moving, your neutrons and protons stop vibrating, and all activity stops. That's extremely cold. At 40 degrees above absolute zero, electrons don't like to move. So that would mean your electricity would not work on your robot, even if you had a fully charged battery, if you don't keep the robot warm. So our challenge is going to be, if we want to mine material in a PSR, we have to have a robot that, first of all, has plenty of power so that it can keep itself warm when it's operating in there. And then it's probably got to warm up that cryogenic ice so it can draw the water out of the lunar soil, and then collect that and then bring that up out of that crater in the permanently shadowed region. Other ways we can make water on the moon, though, is they have found that they have methane, which is a combination of carbon and hydrogen atoms. They also have oxides on the surface of the moon that exist in metal oxides, and there's a lot of that on the surface of the moon. The moon is actually about 45% mass oxygen, but it's not there in an atmosphere. It's all tied up in these oxides in the soil of the moon. So if we could collect the methane that exists in pockets on the moon and collect the oxides off of the metal oxides that exist on the moon, process those, we could make water from that. We can make oxygen to breathe. We could burn the methane with the oxygen in order to have a low-grade rocket fuel, so we could launch rockets off the moon to go explore other areas of the moon. So these are all part of the NASA science that is involved with doing moon exploration. And the reason why we have our future engineers learning how to engineer systems for doing exploration and construction on future moon bases and Mars bases for the next generation of explorers that will be working not only with NASA, but with commercial space systems such as SpaceX, Blue Origin, and others that are planning to go to the moon and do great things. We've heard a lot of talk in the last while too about going to Mars, and I have a great little example. I didn't bring my aids with me to do that training, but I can explain them easy enough to understand. Well, it looks like I'm going to have to stop there because it looks like we're getting ready, maybe, to bring, yes, I think I see it. Yes, we have the University of Minnesota's robot coming in, so I'll get one of their members here. Sweatshirt, so we can see your, there we go, because I want to see that team logo. Yeah. So we've got the University of Minnesota robot coming in to the arena, and They're getting ready for their setup for their hopefully competition run if we don't have any connection issues. Welcome. You are
I'm Anthony.
Anthony. Okay. And that is Brogny.
Yes,
Did I get
Anthony
that right? Brogny. Great. Well, thank you, Anthony, for joining me here
Yeah, no problem.
at the announcers podium as we watch your team get ready to go on this. So tell me a little bit about your team and your robot and what your hopes and expectations are here today.
Yeah, so we're the
And
University
our
of Minnesota.
camera's right there. So,
Perfect.
Okay.
We're the University of Minnesota Lunabotics team. This is our third year competing since COVID. The team's been around for a long time. We competed before COVID, but then kind of took a break during that time. So we came back at the competition at University of Alabama 2 years ago. And then we were at the UCF competition last year.
Yeah.
And then now we're here this year. So we've been making steady improvements each year since we came back. We've been making a lot of progress. And I think this year we have the most promising robot we've had since we came back after COVID. So we've got high hopes, and we're excited to see how our robot runs this year.
Okay. Does your robot have a name?
It does. The name is Cheese Grater.
Cheese grater.
Yes.
Okay. Any Packer fans on the team or
No.
probably not?
Well, one.
One. Okay. The rest of them are probably Vikings fans, right? Definitely Gopher fans, though, right?
Yes, definitely go for fans.
Yes. Excellent.
The name comes from how the surface of the moon looks like cheese, like Swiss trees with all
Wonderful. Yeah.
the craters.
Yeah.
And then we're grading the cheese by digging it up.
Yeah.
Is where the name came from.
I love it. Love it. That's great. That's great. So what are some of the system features on your robot?
Yeah, so we've got a lot of actuators and sensors on the robot. So our drivetrain is a standard tank drivetrain. So we've got 4 fixed wheels, and
Okay.
they each have a direct drive motor, so they each have their own motor with harmonic gearboxes.
Now you're the second team that's referred to that as tank drive, but don't tanks use treads?
Yeah, well,
These are wheels.
right. It's wheels instead of treads, but we call it tank drive because we use tank steering.
Tank
So
well, that's skid steer.
yeah, skid
Okay,
steer. Yeah,
that's skid steer.
we call it tank steer.
Well, see,
steering.
I try to teach my students right terminology and things so that when lay people hear it, they know what to think about. So that's skid steer.
Right.
Okay, we have tank drive because we have tracks on ours. But nonetheless, why skid steer?
So skid steer, I feel like skid steer and tank drive are what most teams use. It's pretty
That's
tried and
true.
tested method.
Yeah.
We actually tried something different last year. So last year at UCF, we had swerve drive, where we had 4 wheel modules, 4 wheel pods, 1 in each quarter. And
Right.
the wheels were independently driven and independently steerable.
Okay.
So if you think of like shopping cart caster wheels where the wheels can change
Yep.
orientation,
Yeah.
so we had that kind of drive last year. And the benefit to that is it's omnidirectional. So we
Yes.
can move in any direction, you can rotate while moving, you can do a bunch of stuff. We figured it would be a lot easier to rotate in place
Yeah.
because skid steer, skid steer with wheels can have some issues
Absolutely.
with rotating
Yeah,
in
it
place.
can.
So we tried this out last year and it worked well enough. It worked all right. But we sort of, when we were planning our design for this year, we weighed all the pros and cons and we determined that it was just too much of a hassle. It was too many complicated moving parts and too high maintenance
Yeah.
compared to this sort of drivetrain.
Well, now here's an interesting thing. How many motors are involved with your skid steer system here? to drive-
4, 1 for each wheel.
One for each wheel. How many motors were involved with your robot last year to drive and steer the
There was
robot?
8, 2
Eight
for
motors.
each wheel.
There's the key thing. And when you stop and think about it, the Perseverance rover and Curiosity rover have no less than 10 motors running their drive system to steer it and drive it. That's 10 motors they have to take aloft, 10 motors they have to control to drive the robot. They're using 4 motors. By comparison, on the tank drive system on the Cardinal Space Mining robot, we have 2. Just 2 motors. Now, of course, the big issue is that each motor has to be sized appropriately so it can move the robot and not stall and damage itself. And so naturally, when you go from 10 to 4 to 2, that motor size has to go up. But hopefully, because you have fewer number of motors, your reliability and your total weight that you have in the system go down. So how much weight did you save with going to this skid steer system on your robot?
I don't know exactly how much we save by going with that. I'm actually a member of the software team mainly, so I know a lot
Oh,
about the software side and the control system, but I
okay.
do know the total weight of our robot this year is 62 kilograms.
62.
And I know it was a lot more last year, but I don't know how much more.
Sure. Just for reference out there, NASA puts a weight cap on the robots of 80 kilograms. We can't weigh more than that. You can weigh as little as you want, but the lighter you are, the harder it is to move material, dig material, and you have to wind up with a very specialized digging system. And then you have the challenge of not having enough weight in order to get enough volume to actually make a difference. You want to have a digging system that's very efficient and can collect a decent amount of material for the battery power that you're going to use. Information that I got a number of years back from NASA, I asked physicist Dr. Phil Metzger, who was affiliated with the Swamp Works at the NASA Kennedy Space Center. He's now a researcher at the University of Central Florida. How much moon dust would they have to dig up in order to have enough oxygen to keep an astronaut alive for a day? And he told me it was 1,000 pounds per astronaut.
Oh,
That
wow.
would have to be dug up. Now, does that sound like a very tall order for these robots? Well, I'll let you know that the Iowa State robot in 2014 went to Hawaii to do a international space mining competition, and in 40 minutes of operation, we dug up 1,000 pounds of material.
Wow.
That was very impressive. Unfortunately for us, West Virginia, who was there competing too, dug up 1,040 pounds in the same period of time, beating us by 40 pounds in 40 minutes of digging. Just didn't, but it was a fun time. We really enjoyed it. Hats off to West Virginia with what they had accomplished at that competition. And we've since seen some teams that can do significantly more. We had one of the teams yesterday, which I'm sure you got to watch, San Diego State University, completely filled up the berm area with a mound that just about hid the robot by the time they got done. It was very impressive. That was a lot of material, and they did that in 30 minutes. And I would really like to know the weight of that mound when they got done with it. It was probably quite a bit. Do you think you guys can do something similar today to that?
I hope so. We'll see. We
Yeah.
do, a big selling point of our design is we do have a big storage capacity for material. So if you look at the robot in the top right image here, we
Yeah.
have basically a big dump truck in the back that all
Yeah.
of our material gets stored in.
Now, how do you get the material out of that box once you have it in there?
Yeah, so it works just like a dump truck. So it's powered by a big linear actuator, electric linear actuator that will tilt the box up. And it's designed mechanically so that as the box tilts up, the door on the back actually opens too in the same
Okay,
motion.
just like a dump truck.
We tilt it back just like a dump truck.
What angle do you go to get the material out?
I'm not sure about that.
Okay, well,
But I do
we'll
know
see.
we also have an agitator motor on the dump box.
Oh, you're going to excite the material a little bit. That
Yes.
helps a lot. Well, just as a reference for all of you out there, in the years that we've been doing this, we found the magic golden angle for getting material out of your dump box is about 50 degrees off a horizontal.
Oh,
For this
interesting.
material. Yeah. If you don't get to that, you got to give it a little help. And in their case, they got a vibrator on it, so they'll probably see that material coming out at a pretty big order. We've done a number of testing. At 50 degrees, the material slides out nice. If you have a diverging box, that is, material releases from the sides and it's free to flow, we could empty our hopper out in about 10 to 12 seconds. With vibration, 2 seconds. It all comes flowing out at once. It's really amazing to watch this lunar material behave. Any sort of energy you put in it, it'll move. It also, if you put too much energy in the surface of the material while you're running, it'll move and you wind up being stuck. So your biggest challenge is this is where the challenge is between track drives, skid steer drives, and then the rotational drives that Anthony was talking about earlier here is that agitation of the material and trying to make sure that you don't get it too excited so it stays compacted and you can drive on it and get where you need to go. So in another minute here, when the setup time is done and the competition run is going, and hopefully the robot is fully connected and operational, we'll get to see how this skid steer system works. So tell me, how many members in your team this year?
Oh, I don't know exactly, but we've got like 14 members, 14
Okay.
members.
And it looks like you have most of them here. That's excellent. Yeah, are you a part of a senior design class or are you a club?
We're not actually. So we're part of the undergraduate robotics club at the University of Minnesota.
Okay. Undergraduates, robotics. I'm keeping all this information down just for fun. Robotics club. So you're a sub element of a larger club.
Yeah, so we've got a
Yes.
club called University of Minnesota Robotics at the university, and we actually have multiple robotics teams under it, and we're one of those teams.
One of those teams. Excellent. What sort of other competitions do you get involved with in that club?
There's a couple we do. So we do this one. We do RoboMaster, the North America division of RoboMaster.
Okay.
We do VexU, which is the
Okay.
collegiate level of Vex Robotics.
Yeah.
And then we also do every winter break we do Robot in 3 days. So that's not really a competition, but that's also something
It's a
we
personal challenge,
participate in.
sounds like that.
Yeah.
A whole lot of hacking and whatnot, and what I like to call TLAR engineering. That's an acronym. It stands for That Looks About Right. And Anthony understands what I'm talking about. And then as engineers too, when we're doing that sort of stuff, maybe we do a good deal of swagging, as we call it. And I won't say all the words in there, but it does involve a little bit of math because it's scientific, but it's basically a guess that we do as engineers. But the last thing we want to do as engineers is we got to do the analysis. We don't want to just build something and say, oh, well, that looks about right. Let's go out and run it and see what it does. Because usually we'll find out, no, it's not about right. Then we have to go run it and test it again. And that takes time and money. And when we're doing something like this, and we have a moving robot, and it's moving quite nicely too. Very good maneuvering.
Yeah, it looks like we're connected and operational.
Wow, it's turning nicely.
Yeah, this kind of drivetrain and these wheels we have do not like to turn on like carpet or hardwood floor, but they turn great on the regolith material we found.
We've got a little robot that doesn't like to turn on carpet either. We hope to bring him out later today, and that is Wally. And we actually designed and built Wally here. It's not the Pixar Wally, but it is a facsimile, or it looks just like Wally, and he acts just like Wally, and we're going to use him for outreach with grade and junior high age students. So looks like you're getting set up to do your mining operation. So tell me, what's your strategy here for doing
Yeah, so
mining?
I believe right here actually we're gonna attempt an autonomous dig and offload.
All right.
So we have a full autonomous procedure that will do a dig cycle, and then it'll drive back a set number of meters into the dump zone, and then it'll do the dump cycle. So we wanted to attempt this right off the bat to see if it'll work, because we've tested it, but we haven't tested it in the real field yet.
Okay, and it looks like just maneuvering in there, you've caused for yourself a little bit of uneven terrain, which will create a challenge for the autonomy
Yeah.
and getting accurate distance travel on there. This is one of the many different difficulties that we have in doing this, because in order to estimate distance, there's several different ways we can do it. So tell me the sort of sensor system you have on your robot in order to estimate distance traveled.
Yeah, so we're actually using visual inertial odometry to determine where we are and how far we've moved. So
Okay, that just went right over my head. Please explain that in layman's terms.
yeah, I can explain it. And first, very quick, I'll explain what we're not using. I feel
Okay.
like a pretty common method of odometry is like wheel encoders.
Yes.
So measuring how far the wheels have spun, how many times the wheels have spun,
Yeah.
and then you can convert that into how far you've driven. But we typically don't use that in this competition because we found that the wheels slip a lot in this material. And
Yeah.
if your wheels are spinning but your robot's not actually moving, it's going to think it's moving even though it's not.
That happened to NASA and a few of their operations of robots up on Mars. So yeah, continue.
So we use a different system. So we use visual inertial odometry, and it looks like we're starting the dig now. But basically on the front of the robot, we have a stereo depth camera with a built-in IMU, inertial measurement unit. So the stereo depth camera is using visual odometry, which means the camera's taking frames, and every pair of camera frames, it can match key points between the frames. So if you have like corners or like like rocks or some sort of like distinct object in the frame, it can
Okay.
match them between the two frames and then determine how far they've moved. And then by that, how far they've moved in the images, you can determine how far the robot must have moved.
Wow, that takes some pretty good coding. Did you get to do that coding?
A lot of this is in like open source packages that we found, and then we like
Okay.
modified it to suit our needs. So
Okay.
that's the visual part. But then there's also an IMU built in.
Yeah.
And the IMU's not so great at knowing like how far we've moved, but it's a lot better at knowing what our heading is and how far we've rotated.
So it'll catch the rotations of the robot, or vertical and horizontal types of sudden movements or accelerations.
Right.
Yeah.
So we basically use a combination of the visual odometry from the camera and the IMU for our odometry system to determine how far we've moved.
And how much accuracy have you found with that system?
I don't have like quantitative metrics to give, but it's pretty accurate from a qualitative standpoint.
Okay, well, I can see from the robot we're still digging. We haven't moved too far, but it is scooping material.
Yeah, our robot digs while stationary.
How does it get more material if it's staying in one place? Is it going deeper?
Yeah. So we
Okay.
actually dig down deep into the ground. We dig a hole into the ground.
And how do you keep from getting stuck in that hole once you have it there?
How do we prevent from
Because you're
driving
going to
into it?
drive back there, and then you're going to drive back out. Now you got this big hole right
Yeah.
there close to the. So now what?
Careful maneuvering. So
Oh.
that's why. So going back into strategy.
Okay. Hey guys, you want to take care of that? Thank you.
So going back into strategy, this is our first run of the competition. So for this first run, we're attempting this auto dig and offload to see if it works and to get those 150 auto points, hopefully.
Uh-huh.
And then after we do this, we're going to go into manual teleoperation for the rest of the match to just cycle as much material as we can.
Yeah.
So once we have this one hole that we are going to have to carefully avoid, unfortunately, where
Yeah.
we have a better strategy of where to dig for the next dig. So for the teleop digs, we're going to start from the back of the dig zone and then work our way forward to the burn zone.
Okay.
So we will have to avoid this one hole, though, unfortunately.
Yeah. Okay. Well, we'll sit here and watch for a little bit and figure out what's going on. We had some background noise here. We have tour groups going through, potential future students coming to Iowa State. It's that time of year where we get the tour groups, so we got some background noise. So we just got to let people know that, hey, we got activity going on in here today, that we need to have it reasonably quiet so we can do our broadcasting for this event. Upstairs too. There's a group upstairs. I can hear them talking over there. Anywho, I'll take a moment. I just see the Caterpillar sign flash here. I want to take a moment to thank our sponsors for this event that made this possible. Caterpillar Corporation, Collins Aerospace. We also have Danfoss and Seek Sensor Systems, Mechdyne, the Iowa Space Grant Consortium, and the Iowa State College of Engineering that has helped made this event possible. So it looks like we're still digging in our hole, doing our autonomy. When does the robot decide it's had enough?
Yeah, so the way that the digging system works is we have this bucket chain. So we have a chain of buckets that's scooping up material.
Yeah.
And this bucket chain is on an arm that's lowered into the ground. So it
Yeah.
sort of swings out and digs like an L-shaped pattern.
Uh-huh.
And the way it's lowered is with linear actuators, electric linear actuators, and they have potentiometers in them, which are sensors that can tell us the position that the motor's at.
Yeah.
So we know what depth the linear actuators are at, basically. So we have, for this autonomous dig at least, we have sort of like a tiered digging system, I guess, where we go to this depth at a certain speed, and then we go to another depth at a certain speed. And then once we get to the final depth, then we stop the digging sequence. And we know we've reached that depth with the potentiometers.
Okay. Well, we're still working away here, digging material. We're about not quite 8 minutes into the run. And so it'll be interesting. How much material does your hopper hold?
I don't have numbers, but it's a lot. We estimated that it's about like 150 points per dump. I know that, but I don't know how many like cubic meters it is.
Well, it's looking like you got quite a bit in there at this point. Unless I'm seeing the side of the hopper.
Yeah, I don't know if there's not really an easy view into it because we have like we have a cover on top of it,
Oh,
that black material, so that
yeah.
we don't have like dust plumage coming out of it. So it is a little hard to see into it.
Okay, so NASA does award points for dust control, do they not?
Yeah.
Yeah. So that's why you've got that in there. What material do you usually test with back home?
Sand, unfortunately.
Sand,
We've got access to a big sand pit, but we don't really have much else.
yeah. Well,
It's better than nothing.
you'll be getting a little vial of ISU1, and you can use that to as a baseline. Actually, you'll be getting a much bigger bottle, so you have enough
Oh,
material
awesome.
to play with. Um, Portland cement, coal fly ash, and sand is the magic combination 531, and that'll be on the big bottle that you get. That will give you a material that behaves exactly like the NASA BP1 that we have here. And we're not on camera, so you folks watching the robot can't see what we're talking about. But I'm showing Anthony some of the things that they can do to set up a similar test chamber like we have here at Iowa State University. It's one of maybe 3 legitimate test chambers for doing this sort of stuff in the United States. Alabama has theirs, which features the same material that we're using here for this competition, the crushed lime rock. I think we're the only chamber in the United States using this Portland cement-based material. And the Swamp Works at the Kennedy Space Center uses the material that we see here in our large container, the BP1, which comes from Arizona. And now our robot has finished digging. It's backed up. It's going to start unloading.
There's the dumping.
And there's the dumping operation, and we'll probably see the vibrator, and there it goes. We got material coming out.
Now it looks like we didn't get to dig down all the way because I noticed the digger was at the same position for a while.
So something you might pass along with your team is, and consider coding, is the best way to mine is to move, because you want to sweep material as you're going. And you could probably guess that the next moves they're going to do is first maneuver out of the way of that hole so they don't get stuck, and now start mining in some other areas. And so it'll be interesting to see what they decide to do here next. Do they go out to the far end and dig there?
It looks like that's where they're heading.
Yeah, very good. Because I don't know if you've noticed on our team shirts that we have, the gray shirts, we have a series of equations back there, and we have the phrase on there. It says, "Can you dig it?" And then all of the equations on there. It's much like NASA has a T-shirt you can buy at the Kennedy Space Center that says, "What part of this don't you understand?" It's all of the mathematics for doing space flight, like inertia, planetary maneuvering, and the like. But in our case, what it is all of the mathematical formulas for designing a mining operation and understanding how much power do you need, how much material you're going to pick up, what's your mining efficiency and stuff. And the big secret here is swept area, what you do in your mine. So you don't want to just sit in one space and just dig a hole unless you're going down. But see, now you're creating swept area as you're digging down. Or you translate, go across the surface, dig up more material. And then, of course, you have a place to put it once you've dug it up. And one of the other measures is mining efficiency, because as our scoops go in and we scoop up material, how much of that material do we get in our hopper versus how much falls out back on the ground again?
Right.
One of the big things that we worked through the years was our mining efficiency, because our first successful robot that won the mining part of the competition in 2012, but we found up a half point shy of winning the grand prize because Alabama beat us out with just that little bit of weight and autonomy. We were about 30% efficient on mining, meaning that of the 100% of material that we swept up, 30% got in the hopper. The rest of it went back down into the trench that we were digging. And we could figure that out by measuring the depth and the width of the trench, and then measuring the material that was there, that was sitting in the trench that had been dumped back into it. And by volume, 70% was back in the trench. The next year, we changed our angle a little bit, and we wound up, lo and behold, because that miner system was set vertical, and we had to have enough speed to throw the material out of the buckets to get it in. And then our bucket angle was wrong too. So we were going so
no.
fast that some material got trapped in the bucket. So when the bucket's headed vertically down, now the material was able to fall free. The next year we put it at 10 degrees. What do you think our efficiency went to after that?
A lot higher.
Well, it went higher, but not high enough.
Oh no,
Yeah, we went from 30 to 50%.
that's a good increase.
It's a nice increase, and with that robot, we were able to not only win the mining competition, but we won the grand prize that year too.
Oh,
with
wow.
What we did, 2013, and that was our robot by the name of Hermes 1. Then the next year we came back with Hermes 2, and we actually tilted our bucket ladder back at 20 degrees, and our mining efficiency went up to 70%,
Oh,
and did a slight change on our bucket angle. And it looks like we've got another dig here, and he's heading back, and he got past the hole. Oh, there you are in that hole, but you got out of it. That's good. That's very good. So you didn't make that hole too deep that you can't drive through it.
yeah. Luckily, we've got nice big wheels.
Yes, those
there's a little
are
flexibility
nice
there.
looking wheels on that robot. And so here goes the dump. We'll see how much material we have. And a much better pile than the last dump, it looks like.
Yeah, it looks a little bigger this time.
Yeah. And we're halfway through our 30 minutes. So that's a good start. One of the key issues on this is, of course, sitting time. And if you're sitting still, you're not being productive. And so actuator speed, translation speed, transport speed, getting out and back is an important item.
Yeah.
So yeah, we'll see what they do here for the next run. We got 14 minutes. Look, he's stopping shy of that hole.
Hopefully, we
Come
can
up-
get another 2 or 3 digs in before the run ends. I
I
think
would imagine you very well will.
the
Yeah.
first dig took a little longer than I should have because I think it got stuck on something and wasn't able to go all the way down.
Now I see a lot of labels on your robot. Who are some of your sponsors for your team this year?
Yeah, so some of our sponsors are the Minnesota Space Grant Consortium, Medtronic, Gene Haas Foundation, the Student Services Fee, which is like our university student services fee.
Okay.
We got EMJ, supplies all of our metal, all of our aluminum and steel for the robot.
Okay.
And I believe those are all of them that are on the robot there.
So usually it takes a good budget to build a robot like this. How much do you think you spent on building this robot this year?
Yeah, well, it's hard to know, to be honest, because we reuse a lot of components from previous years. So
we do too, so-
all of the electronics and the motor controllers and computers and stuff, for instance, we reuse from past years, and that's
Yeah.
one of the more expensive parts. In terms of metal, I think we got like probably $1,500 to $2,000 of metal. We have some steel parts, like the digging buckets are steel, but it's mostly aluminum to save weight. Yeah, electronics. If I had to guess, I'd say all of the electronics combined are probably like $4,000 to $5,000, but we reuse most of that from previous years.
Yeah.
And we've got 3D printed parts too. Our wheels are actually 3D printed on our own printers. We had to print them in 3 separate pieces so that they could fit on the build volume.
Ah.
And then they snapped together, and then we coated it in like an epoxy coating. And
Oh,
then we have
interesting.
aluminum metal faceplate to hold the pieces together.
I'll have to come down and take a look at that. That sounds very interesting. Nice piece of engineering.
Yeah, thank you.
Yeah. So if you had to take a guess altogether, if you wanted to build this robot from scratch, all new components, what do you think you'd be spending?
This is just a rough ballpark, so it could be off, but I'd have to guess $10,000.
I would
10 to 12 maybe.
I would say a pretty good guess. That's what we've had to spend in years past. Because a lot of times we'll wind up building an entirely new robot in the years that we've done this. And usually when we've done that, the cost has varied between $7,000 and there was a couple years we decided to build 3 robots, one for
Wow.
test and 2 for competition. We were going to run 2 robots at the same time. And that year we wound up spending $15,000 on
Oh,
building a
wow.
robot. So this is not a cheap endeavor. We usually wind up spending more money than the SAE Baja team does on building their vehicle. But I'm jealous at the same time. Our Baja team here has some very good machinists, and if you get a chance, our student build areas are down in the basement, and we got some windows in there so you can see the vehicles down there that they have. They build some very beautiful gearboxes for their vehicles. They make their own transmissions
Oh,
that go
wow.
in the Baja car, and it's all CNC machine and then polished, and it's just a work of art. We had a pretty good competition run this year out of about 100 teams, I believe, competing. Our Baja team did place in the top 20. So congratulations to them on a good run. Our Formula team, I haven't had a chance to hear how they're doing, and they're going to be doing a big switch next year. They're going to be doing an electric vehicle
Oh,
for
nice.
SAE Formula rather than an internal combustion engine, which makes me kind of sad because I'm kind of a purist, because my belief is a real car runs on gas and it has a manual transmission. So, but nonetheless, that is the wave of the future, electric drive and the opportunities that offers. And of course, do you think we could run an IC engine on the moon? Why
No.
not?
Um, that's a good
See, that
question.
I'm testing him as an engineer.
I'm a
what-
computer science major.
Oh, you
so
are?
I'm on the
Okay,
software
I'm
side of
sorry. I'm
things.
putting you outside your comfort zone.
Just have to point that
My
out.
apologies. Well, first of all, the moon has no atmosphere, which means there's no oxygen which to burn with. So we'd have to bring our own oxygen, and then second of all, it's in a vacuum. So unless we had a way of pressurizing, getting the oxygen and the fuel into the combustion chamber of the engine, it's not running. But essentially, yes, we could run an IC engine on the moon, but it's going to take a lot of extra engineering to do it, because the combustion processes are very much the same as the rocket motors, only that the rocket motors do it at a much higher volumetric rate. To give you an idea, I have this fun little thing that I show my students. It's a little slideshow called "This is Acceleration." We talk about how fast things can go and how much horsepower, and it's a comparison between a 200-mile-an-hour Lingenfelter Corvette with 500 plus horsepower going 200 miles an hour, covering a quarter mile at full speed, compared to a top A fuel dragster that has an 11,000 horsepower 500 cubic inch V8 running on nitromethane that's starting from 0 miles per hour, and a 747 and a space shuttle. And by the numbers, this is really fascinating, because the top fuel dragster is going to accelerate at such a high rate that it's actually moving faster than in G-force than what most fighter pilots feel. And so it'll get at the end of the quarter mile before the Corvette does by almost a full second.
Wow.
And the Corvette's going 200 miles an hour, but that top fuel dragster is going to be going at 320 to 360 miles an hour these days. It's just incredible velocities and accelerations. Fuel consumption rate on that top fuel dragster is going to be at a very high rate. It's going to be 1.5 gallons per second that it's burning fuel. By comparison, a 747 at cruise, very big aircraft, is burning 1.2 gallons per second at cruise. So this one car is burning more fuel than all 4 engines on a 747 is burning.
Wow.
But not to be outdone, the space shuttle engine, the RS-25 engines that launched the space shuttle, burning liquid hydrogen and liquid oxygen, has a fuel nozzle in the cone of the rocket about the size of a shower head. So that's about 6 inches in diameter. And that is pushing out fuel at the velocity of 450 gallons per second.
Wow.
Out of that one nozzle. And that is fuel consumption right there, and a whole lot of horsepower to make that happen. And then that burns and creates the thrust, millions of pounds of thrust that will launch the rocket into space. We put that same motor on the back of the dragster. I don't think the results would be very pretty. So, so that's why nobody's done that yet. They put great big jet fighter engines on the back of dragsters and run them down the drag strip, but they're not making the same level of energy as a rocket motor on a space shuttle would be. So,
Yeah.
yeah. So back to energy here. We got 4 46 minutes and 47 seconds. We're digging another hole here for the University of Minnesota. Looks like they've done 4 deposits in the berm area. They're getting a nice little berm built. And they've not gotten stuck yet. The robot is operating nicely. And so this is exciting to see.
Yeah, it looks like everything's operating well, but we're not quite getting the digging depth that we want. It looks like we should be going deeper and collecting more material. So I wonder if there's something with like the later stages of our dig that's going wrong that we'll have to take a look at after this.
Yeah, sometimes things get jammed up. You get some material where you don't want it to be, or maybe an actuator gets bound up and it just doesn't want to move. That was our problem in our first run. We actually had a wire that got pinched, and so our depth control actuators weren't running because they weren't getting the electricity they needed to operate. So we're hoping on our second run everything goes as planned, and we'll see whether or not we can get as much material into the berm areas as San Diego State or New Mexico Tech. Very impressive runs in those 2 teams. For those that are curious to know now at this point, from what we've seen on runs, and I'll get scores off of this run as well, the San Diego State University Creed team did a run and got 852 points. I want to find out just exactly how much regolith they deposited into there. That's a very good run. The New Mexico Tech Minor 49ers, I love the name of that group, 767 points in their mining run. One of our other rookie teams in the competition, we have 2 here. We got Northeastern University, but Youngstown State University, very cute little robot. Did a very nice job of operating in the arena, made it look very routine, almost like a Wally robot. But it's very small, it's very light, it's very compact, very small shovel on it, but it managed to score 428 points. It got a fair amount of material in there, but it's going to have to work a lot harder. It's going to catch up with the San Diego State team. Arkansas Razorbots, they wound up with 262 points. They had some operational problems and had to stop their run early. And then our own hometown team here, Cardinal Space Mining, with their issues, had a score of 222 points, but they're not actually competing, but we're going ahead and keeping track of things just to see how things stack up. You know, being last year's grand champions and winner of the mining award, we wanted to see how these other teams stack up by comparison. But of course that relies on us to have a fully operational robot, which we did not. And so we got some work cut out for us as well. But that's all part of space mining. It's all the technical challenges that we have with getting everything to work as planned. And you know, as I like to tell, this is something that is a very good training ground for all our engineering students, because they're constantly dealing with problems, and you can't just hope the problems go away. As I told one of my senior design teams, I asked him, well, how there's a design going? And he said, well, I hope it's going to work. And I said, wait a minute. There's no hoping here. You don't hope in engineering. You engineer it. You figure it out. You analyze it. You build, you test. We don't hope it's going to work. We have to know it's going to work. And the same thing here with what we do here with space mining. We design, we build, we test, and we can hope. But if it doesn't work, then we got to go figure it out. We're the engineers. We got to make it work. That's what we're tasked with doing. Just like good old Montgomery Scott and Star Trek, when Captain Kirk needed more power, it was up to Scotty to give him that power and get them out of whatever situation they're in. And this young generation of future engineers is going to be under the same pressures, but I know they will be able to handle it well, especially with going through something like this, because competitions like this are certainly great big pressure cookers, are they not?
Yeah.
Yeah,
It's a tough problem to solve.
Yeah, well, it's kind of stressful here watching a robot, hoping to see what it's going to do, and maybe it works and maybe it doesn't work. We certainly had some of the other teams here watching, and then the robot not move at all because they can't get it connected. That's pretty stressful to have that watch happen. One year we were at competition and our robot drove into the arena, and we couldn't get it connected, and we sat there for half of the run not doing anything, and then all of a sudden it came on. Unfortunately, something got messed up at the control commands, and the actuators that were supposed to pick up the hopper for the robot so it could drive. One went up and the other went down, and it twisted the robot and broke
Oh,
the frame.
no.
I almost broke the robot in half. And so then we had to fix the robot, and then we got it repaired and got it into the arena for the second run, and then we couldn't get the communication to work at all. And that was a heartbreaking year. We only had one controls person, and that was very devastating for us. Well, we got about a minute and 20 seconds left. They're doing a little digging close to home here. Looks like my guess is, yep, when they get close to a minute, they're going to back up and make their last dump. I think they got a very nice run going here with the amount of material collected, and they're backing up. They're going to do their last deposit here. This is where that slow actuator is a little stressful. As you got the seconds ticking down, you want to get all that material out of there right away. But that's part of the science of doing the space mine. I have to say your gate opens very nicely on this as you go dump. It opens without very little effort. And yeah, it's making best use of your time, having good translation speeds and everything, because in a competition run like this, time is of the essence. But in an actual operation on the moon, it's more about energy usage.
Right.
And sometimes slow's not so bad because it doesn't require too much energy. So, all right. Well, Anthony, thank you for sitting with us. I come back and let me know what the
score
debriefing
is.
is on your robot, and what your mission control team had to say about the run, the good, the bad, and what your goals are for the second run when you go there. Congratulations on a good run again.
Yeah, thanks for having me
Yeah,
on.
no, thank you for being here at CoSMiC. We really appreciate all the teams that are here making this event what it is. Okay.
Yeah, thank you.
Okay, well, that was the University of Minnesota's run. It looks like they had a successful competition run, so congratulations to them. And looks like the next run up, I'm going to go ahead and sign off here for the moment. All right, I just got information from our great leadership team that the next up, University of Illinois at Urbana-Champaign is going to do a test run, and then we'll be taking a break for lunch and then get our next competition runs coming back in. It looks like after that, it will be Cardinal Space Mining doing a second competition run as a demonstration, not as a competition, followed by Illinois Robotics and Space. So I'm going to go ahead and sign off for a few minutes. Let you watch our wonderful box team of Jesus and Walter get the robot out. We'll get a score on the material that is deposited there, and we'll get the arena prepped. Looks like they'll have a little digging and raking to do to get everything ready for UIUC's practice run. This is Jim Heisey for the CoSMiC event at Iowa State University. Thank you for watching. Well, I don't have any stepatorium, so I'm not going to turn that mic on right now. This is for the stepatorium. This is for okay. All right. Well, welcome back. We're just getting ready to do the second run for the Cardinal Space Mining Club and their robot. And what was just reported there? Okay. Okay. So they'll be loading the Cardinal Space Mining robot Lance 1 into the arena soon to make their run. Just to give you some numbers, I went and checked back with the judges on our space mining because I got the points, but I was really curious to understand how much material was collected. So the team with the lead points, San Diego State University Team Creed, 852 points. They collected 147.4 liters of material deposited into the berm, but then it's also a question of weight and other factors and energy used that factor into your score. The New Mexico Tech Minor 49ers scored 767 points. However, they collected 181.5 liters of material in their run. The next team are one of our rookie teams that we're so excited to have here, Youngstown State University out of Ohio. They scored 428 points. They have a wonderfully light and small robot. Didn't collect much material, but their energy usage was low, so they had a good score. 41.3 liters collected. Still, given what they had for size of robot compared to the other twos, a potentially very efficient little mining robot. Next, the Razorbot from the University of Arkansas didn't collect much material. They had some technical issues, but they did score 262 points. But they collected 0.016 liters of material according to the LiDAR. And then finally, ISU Cardinal Space Mining Club, their Lance 1 robot scored 222 points. We collected 51 liters of material. We also had some technical issues with controlling our actuator for dig depth, and so they had to do some very creative driving. For a while, they were driving circles. I call it doing the Billy Preston, but actually what they were trying to do is to mound up enough material so that they could get enough material collected into the hopper to make a good mound in the berm building area, which they managed to do. 51 liters is a good start. Actually, I'm sorry, it's 57 liters that they collected. So we're hoping to see here a much better run out of Lance 1. They informed me that they got the actuators running properly this time. So we should see some very interesting driving skill going on here. The moving of rocks into the berm area, collecting a significant amount of material and getting that deposited. It looks like maybe they've done a little work too on keeping the material in the hopper rather than putting half of it on top of the robot, which they did on their last run. So we'll see how it goes here. So our crew in the box is getting everything ready to go. That's what we've been calling our lunar arena, the box. This was designed and built by our club, by our engineering students here at Iowa State. They constructed this on their own and then had the help of facilities to go pick up 22 tons of crushed lime rock from Martin Marietta, the Ames mine. And we were told that planned for 2 hours of material transfer time, but my goodness, our facilities team that helped us get this loaded in here, I was informed they did it in about 10 minutes time. 22 tons in 10 minutes time. That's very impressive. So looks like we're ready to go. We have another 8.5 minutes or 8 minutes and 50 seconds of setup time to check to see if they're connected with the robot. Our driving team is in mission control at the opposite corner of the building. So they're about 200 feet away. There they are. And they'll be getting themselves connected to the robot, testing the systems, make sure everything's running ready to go. And then hopefully we'll have a good run out of this. Last year, this robot competed at NASA. It collected well over 200 liters of material. deposit in there, moved 3 rocks, and took first place in the mining. And we wound up tying with the University of Alabama for the grand prize at the NASA competition. This year, unfortunately, due to some technicalities, we didn't get in, but so did several other teams. So we thought it would be a great opportunity to help the other schools and ourselves have a productive year. And so we came up with the idea of running our own space mining competition called CoSMiC here at Iowa State University. So I am very grateful to ISU administration, College of Engineering, the Iowa Space Grant Consortium, and for giving us the opportunity to run this competition here at Iowa State. We have 11 teams from across the United States. We have Sonoma State University out of California, Youngstown State University out of Ohio, University of North Dakota, the UND Lubonics team, San Diego State University, Team Creed. We have North Dakota State University, the Bison Robotics. We have University of Illinois Urbana-Champaign. I usually like to say it the other way around. Illinois Robotics and Space. We have Northeastern University out of Boston, the NU Lunabotics team. We have the University of Minnesota team. We have Iowa State University, the Cardinal Space Mining Club. We also have New Mexico Institute of Mining and Technology, and their team's name is Miner 49ers. I have a lot of fun with that one. We have the Virginia Polytechnic Institute and State University, otherwise known as Virginia Tech, and they're the astrobotics team. And I was visiting with them yesterday, and come to find out they actually have 2 robots. One did make it into the NASA competition. Unfortunately, it did not place, but they brought their second team here, and we're very grateful to have them here. And then lastly, University of Arkansas Razorbots, and they've we'll be doing another run sometime today or tomorrow. And right now we're getting ready to run the ISU Cardinal Space Mining Club Lance 1 robot in our lunar arena. So special thanks again to our sponsors, Caterpillar, Collins Aerospace, Danfoss, Mechdyne, Seek Sensor Systems, Iowa Space Grant Consortium, and the Iowa State University College of Engineering for sponsoring us and allowing us to make this possible. We do have other sponsors for the club that help us with building our robot. Again, ISGC, along with Boeing Corporation and Vermeer, who have given us money to support our work on the robot. But those are the sponsors I named off earlier that helped us with this competition. So we're very grateful to be able to do this for an inaugural event, and who knows, maybe we'll do it again next year, but hopefully you will see the Iowa State team at NASA in the Kennedy Space Center Visitors Complex at the Space Education Center in their lunar arena competing next year, and hopefully can defend our title again. Last year we were co-champions with the University of Alabama, and the year before that we were the grand champions in the competition, and we look forward to having the opportunity to compete again. But we're very grateful to be here and have these teams here. It's been a wonderful time. The energy in the room has been fantastic when they've been running, and yeah, I'm gonna not right now. Oh yeah, when we get ready to run, Anna, why don't you go ahead and get up here now? Yeah, we'll get you. I don't have a camera on us right now, but yeah. So I'm going to be joined here during the run with Anna Overman, one of our team members who graduated in December, but she's hung around to help the club and do wonderful things, and she's done a lot of work in the club over the years. With doing things. In fact, what were some of the leadership positions that you've held over the years with our club?
Yeah, so my first leadership position was the safety officer, and then I was a sub-team lead, and I did that for, I think, a full year, as well as the safety officer position with that. And then I was the mechanical co-lead for a year, and now I'm helping with competition planning.
Yes, and things have been working great. So
Yeah, it's gone very well so far. Hopefully it continues that way.
Yeah. So What were some of your favorite memories out of all the years we've been doing this,
Um,
aside from pushing me in the pool?
well, that's a tradition. Every year that we win or we do really well or we're really proud of ourselves at competition, Heisey allows us to push him in the pool at our hotel or Airbnb. That's always a fun experience. But I would say the NASA trips have been my favorite. It's a whirlwind of a week when it happens, but there's so many memories that happen, and yeah, it's late nights and it's hard work, but it's a ton of fun.
Yeah. And you guys make me very proud with everything that you accomplish on this. It's been a joy to work with all of the club members in here and see the great things that you get to do. It's been wonderful. So you said you were a team lead. What systems were you working on?
I was working on our hopper system. So this was back when we were mining for the gravel underneath of the dusty simulant, and that year we had changed from just like a regular box hopper with a bucket ladder to feed out of it to a trenching system that would simply throw the material onto we had a flat food grade conveyor belt that had about a centimeter of gap in between each of the spokes.
Yeah, so really kind of a wire belt, wasn't it?
Yeah,
Yeah.
yeah. And the idea with that was that as it would pull up the dusty material, it would just fall right through and only capture the scoreable rocks underneath of there. And then we could mine for longer and do less sorties for more points.
Yeah. And how did we do that year?
I believe we won. That was the year we were, it was the Caterpillar competition at Alabama. We won
Yeah.
first place. Yeah.
Yeah, that was a good year. What do you remember the name we had about that? Was that Dionysus or was it Atlas?
I believe that one was Dionysus.
Dionysus. Okay. And we're rolling here, so our robot is now on its competition run. Looks like we've done a few changes as far as where we're doing our dust mitigation. We normally have a screen around the back to control the flow of the material. This ag lime doesn't flow as bad as our ISU1 material does. Talk about some of the challenges about that.
Yeah, so the skirt, as we call it, on that we had on the back of our robot for our first run, the idea of that was to basically hold the regolith in place as we were dumping so it doesn't spread out flat. We did a bunch of testing in our lunar testing chamber to test from what heights we could drop it and how it would react. The 18 inches that we are above the ground right now, when we tested a dump with that, it went completely flat and it even compacted the material underneath of it. So we would have gotten negative berm volume for that. So having with a looser material that flows more like our ISU1, it was very important to have that skirt on there to kind of contain it and hold it in.
Okay, well, I'm going to take a second here. I'm going to have you step aside, but I want you to stick around because once you come
I will-
back as this run goes, because I've got our university provost here, Jason Keith, and I'd like to pull him over here if I could to ask him a few questions and maybe make a few statements. So, John, could you go over there and have Dr. Keith come over? Thank you. So, Dr. Keith, if you wouldn't mind, I'd like to get you on here. So I have with me today, while our robot is running, our university provost, Dr. Jason Keith, and we're very pleased to have him here to see what's going on with the conference. What was your impression over in the Luna pits over there with all the teams?
It's amazing to see all the work that all the students are putting into this, and it's so hard to organize these sort of events. So, thank you and all the students at Iowa State here that put extra time in to put on a tremendous competition.
Well, thank you. We're happy just to have support to do these sorts of things, and of course, what it means to the students too, with what they learn. And I just nudge them. That's my job, just to be a nudger, to get them to do things. But
My job's very similar, although I consider myself a matchmaker and a cheerleader.
Yes,
It's like
and
we need to find opportunities, connect people together,
Yeah.
and then celebrate
yeah,
success.
so-
And it does sometimes require a little bit of nudging or pleading in some
Yes,
instances.
certainly that. Of course, we're really thankful to have this wonderful facility here, the Student Innovation Center, to be able to run this in. And of course, Iowa State, we're really big about innovation, and we certainly see a lot of that here with what all the teams are designing and competing with in the future of industry, particularly interrelated to space. So I'm curious to know from you, what has been your exposure to like the future of industries such as this, and the role that Iowa State plays in innovation toward that?
Yeah, absolutely. That's a great question. And I was telling some of the students, like, this gave me the great tour. I started working here 9.5 months ago, but it was a little bit over a year ago when I was on the Iowa State campus for the first time. And I came on
Yeah.
a Sunday before my interview, which started Monday morning.
Yeah.
And I had an incredible time just walking around the entire campus. But I spent extra time inside of the Student Innovation Center just looking to see what sort of facilities were available here. So at that time, I was dean of the Bagley College of Engineering at Mississippi State, and we were going through a process of taking some of our laboratory spaces and some of our older facilities and creating an engineering student center, creating a space for integration of the academic enterprise with that of industry to solve real world projects. Just
Yeah.
like Iowa State, Mississippi State is also a land grant university. And so the land grant model is rooted on the idea of bringing in potential students and giving them the skills that they
Yeah.
need to be successful after they graduate. And
Yeah.
in my opinion, land grant universities are the best type of university to provide that type of training, because
Yeah.
it's not just going to class and seeing a bunch of equations. It's, let's show you how to apply these equations in the real world by doing regular laboratory experiences, by having capstone and
Yeah.
senior design experiences, by doing co-ops and internships, being involved in student organizations, as well as other experiential learning activities such as
Yes.
student competition teams, or coming up with your own idea. And that's what's incredible
Yeah.
about the Student Innovation Center here at Iowa State, in that each college has a presence here. And so it doesn't matter what your major is, you
Yeah.
can come in and come up with a new idea and really run with it.
That's great. Just some fun facts here. I am a alumnus of this university, and when I was an undergraduate here, I was on the very first SAE Baja team. And we didn't have anything to work with, so we had to find a little corner in some place in the mechanical engineering to build. And I'd like to think of all of that we did there has led to all of this. And I'm so thrilled to see all the different competition teams that we have and the hands-on that they're doing. When I finished my time in industry and got talked into coming here to teach by then Associate Dean Ted Okishi, thank you, Dr. Okishi, because he told me, "Oh, Jim, you don't need to retire to come teach. You just need to come right now and teach." So I thought was a great comment. A couple of years after getting here, he and Dr. Wickert helped me get the ME Capstone program established. And since the fall of 2008, we've been doing just as you said, working with CIRRUS, our Center for Industrial Research and Service, with bringing projects in to the classroom that our students will work on. And since that time, we have had the economic impact for just the state projects that we've done for the state of Iowa has been valued at over $90 million. And we directly through the projects that our students have worked on have created over 210 jobs for Iowans in the state with doing that. And I'm so proud of our students for doing that sort of work. And I just had a chance to talk with one of the other faculty advisors here today from San Diego State. He's now actually doing work with Winnebago. Their corporate offices are up in Minnesota. He's out in California. The project we did was for the company their facility in Forest City, and it had to do with aerodynamics on trailers. And he said the quality of work that our students did was spot on and really helped them with taking the work they were doing to the next step to develop the next generation of travel trailers that would work with electric vehicles. So I think it's an excellent example of the sorts of things that we can do as a land-grant university with promoting and giving our students a chance to really learn what engineering is about and making them prepared for the 21st century.
Many
and being-
times,
yeah.
someone will be working on a project so long that they'll kind of have a set way of doing things. And when
Yeah.
you bring in a group of students to look at it, they'll have a different angle or
Fresh
viewpoint on
fresh
that.
approach,
The fresh
yeah.
ideas allows for innovation to take place.
Yeah, and the fun thing we do is we'll typically put 2 teams on an industry project, so there's a parallel path of thoughts, a little bit of trash talk going on between the teams. You know, I can do it better, and
Healthy
a very-
competition.
yes, and we get some very good results out of it, and we have a few patents to show for it as well now after a few years of doing this, and looking forward to what the next decade will bring for us as we expand our operations. And
Yeah, and as our students generate these ideas that could result in patentable ideas,
yeah,
there's the Papa John Center at the Research Park, right next, same building as Cirrus.
yeah,
And there's 1,000,000 square feet of space there. And so it's an opportunity if a student wants to, after they graduate from Iowa State, they could start their own business and they can stay right here in Ames
yeah.
and do that. And that helps make Iowa's economy stronger.
Well, now you've given me a charge as to what I need to work on. And the next big step in everything that I've been doing with coordinating the capstone program is to figure out how we can take advantage of things like the ISU Startup Factory and the Papa John Center to help some of these students to create the next big adventure in their careers as they come out of here. Well, hey, I want to thank you so much. I
Thank
know you're a
you.
busy guy. Thank you so much for taking
the
some time.
tour and,
Yes.
and nice visiting with you. And thank you for
Likewise.
your leadership to our students.
Well, I'm just doing what I love to do with these students. They inspire me every day, and I think I have the best job in the world. Doing
Well, we
what I
can take
teach our-
notes and talk about that because
Okay.
I like mine too.
Very good. Well, thank you
Yeah,
so
thanks a
much.
lot.
All right.
Enjoyed the visit.
Thank you. That was Dr. Jason Keith, our provost at Iowa State University, vice president, and we're really thrilled to have him here helping us.
We're going to take a
continue us on.
selfie here too. on the
Oh,
little
okay.
camera over there. I'm going to do
Absolutely.
that.
Yeah.
So look
Okay.
over there and smile.
Okay, I'll do that. I'll look at the camera, and the camera's right there.
Yeah,
There we
so
go.
there you are.
All right.
See?
All right.
Thank you again.
Thank you, sir. All
I'll
right.
get you on
take care. Okay. Did Anna just? Oh, there you are, Anna. Come back over. How are we doing so far? Yeah.
We're doing pretty good. I wasn't entirely watching. I got a call about the competition.
Well, looking at it here, it looks like we've got a good start on a mound, and we're just a little over a third of the way into the run.
Yep.
And we're doing a very nice dig path here.
Mm-hmm.
Looks like our conveyor speed isn't too fast, but it's at a good clip. And I didn't get a chance to see how the dirt's coming out on that when they go to dump it, but it looks like it's behaving itself pretty well.
Yes, and this time we have the linear actuators connected, so we can actually dig some material and as well as offload, which is good.
Offload and maybe push a rock or two. Have we done it?
We'll try. I don't. The one on the edge there seems a little close to the wall. I'm not sure if we can get to that. It's got to be right in between the tracks is where
It's not quite
our push
reachable.
bar is.
Yeah, looks like he's pulling up to come back to unload. He's going to plunge back down and take another stab. He didn't want to dig into a trench he already created. I guess the nice thing about this material, because we got crushed ag lime rock, we don't have any of those big rocks in there like we have in NASA.
Nope. Yeah, last year with this robot, we were going through our mining run and we hit a rock, and from the cameras all we could see was oh, it looks like there's a couple of blank spaces in there by the belt.
Yeah.
Turns out we had sheared off a couple of our buckets, and then didn't realize that until we came back. And then the next team who ran was walking back from their run. they hand us the bucket of ours that they digged up
Yeah.
with the
Wow.
robot.
Yeah, one of the fun phrases we have on the back of our club T-shirts most years is "Beware the rock."
Mm-hmm.
Yeah, because they're in there, and we've watched many other teams hit these rocks and destroy their robot. Or
Mm-hmm.
my favorite is teams that show up with an auger system, thinking that they're just going to auger like a post hole digger, and then they hit these rocks in the very abrasive material, and they wind up destroying a motor. Wow, that's quite a load
Mm-hmm.
that they got. Well, that's great. Maybe we can outdo our first run. I think we
Let's-
already have.
Oh yeah, for sure.
So looks like he's going to line up for another. Gonna put her down and just start digging from there.
Yep. Yeah, and so we also have a lidar, 3D lidar system on the front of our robot there, and it's angled down a little bit to get just a nice view of the ground right in front of us. We're not attempting autonomy traversal
Okay.
this year round, but we are actively working on it. That sensor was actually donated by CoSMiC, the sensors, and we got it last year, and I know the controls team has had a lot of fun figuring it out and getting the robot to actually see what was there. The year before that, so 2 years ago, we attempted to use two different 2D lidars, one looking out across the surface of the regolith, and then one at like a 30-degree angle down, to try and make our own version of a 3D lidar, but it was not as successful as we hoped. The 3D lidar definitely works a lot better.
Yeah. Who's ever doing the driving there? I think who's doing the driving there in the.
I believe that's Sam.
I'll have to talk with Sam about efficient mining operations because
Yeah, he doesn't need to be turning around.
He doesn't need to be turning around. He needs to just go straight back and forth.
Yep.
Yeah. And
Oh, I'm being told that they took off the camera that we had mounted on the back, so they don't know where they're at in relation to the berm when they back up.
oh, well that could be a problem.
That would make sense.
Yeah. And so they're trying to maximize points by using minimum cameras from the arena. It's kind of important to have that
Yep.
front camera.
Yep.
It's kind of fun though too to drive the robot if you've got using the robot's eyes
Yep.
and seeing what it does,
Definitely.
as opposed to looking at it from a picture in the arena,
Yeah.
because you really get a sense of flying with the robot, so to speak, as you're driving it. So it becomes a lot easier to see what you're doing. So he's probably taking a look now to seeing how much material he has in the berm, would be my guess.
Mm-hmm.
Yeah.
Yep.
Deciding what they need to do. So now,
If they're gonna attempt a rock or not.
yeah.
Looks like that one right in between the traversal and the mining zone there
Yeah.
might be a good one to go after if they want to.
Yeah. Better not stop and
Yeah.
think too long here. Time's a wasting.
Yeah. One of the issues that we face with our robot is that it is very large.
Yeah.
It is almost exactly at the size constraints, maybe about an inch or so under on all dimensions, but we cut it pretty close to try and maximize the amount of regolith we're able to get per sortie.
Yeah.
But it also comes with its own challenges because it's not a very large space that we're running in, and with all the rocks and everything and the walls to avoid, it's hard to maneuver something that big, especially with tank drive.
Yeah. I was talking with one of the other teams this morning. He said they had tank drive, but they had 4 wheels. I said, that's not a tank drive. That's skid steer. This is tank drive,
Yep.
using a track system. And then we discussed about the number of motors and the number of motors it takes to drive a robot. And one of the reasons well, you can explain why do we use a track system?
You may have seen from some of the other runs. I haven't been watching all that much, but the wheels, there's only one point of contact on the ground for each of them. So if they spin out and don't get enough traction, they will dig themselves in and potentially bury their robot and be unable to move. But with the tracks, there's a lot greater surface on the regolith, a lot more traction force. So we're able to just glide right on top of it. And if we do get stuck in, like down in a crater or something, we're able to pull ourselves out. We're also using Falcon 500s on our drivetrain, so they're pretty powerful motors for that. I think we've done some testing. We measured, I think, 240 Newton meters of force that those tracks can put out.
Yeah.
We have a member that's convinced our robot can pull a car, so we'll.
Well, they have to have quite a load in the hopper. We're going to pull the car, and the
Oh,
car
no
better be
kidding.
on a smooth, very smooth surface
Yes, yes.
with a lot of pressure in the tires.
Uh-huh.
It's kind of interesting to see here. We seem to be having some issues with the robot. We're
Yes.
doing some coding.
I know, just a few days ago, we were having some issues with some of the motors just throwing random errors, and then all of them threw every error.
Oh my.
And I think what happened was one of the wires got pinched, and while they were doing repairs, and disconnected. And so they had to go in and put a new wire in there, and everything seemed to be working after that. But we've also had some issues with the motor in running the hopper belt overheating and going into thermal shutdown.
Oh, okay.
But they should still be able to mine if that's the case.
Yeah. Well, I noticed that the bucket ladder, the mining apparatus on this robot, was running intermittently, and maybe it's a case of that. Maybe they did overheat something in there, because I noticed too they were digging at a little slower speed, and for those who aren't familiar with electric motors, they have an optimal point where they run, and where you can keep them cool, but they provide a lot of power. If you run them too slow and pull them too hard, they'll overheat.
Yeah,
And
definitely.
so you really want to make sure that you're running the motor somewhere past its peak power point, where you're up toward the max speed, but not down to the max power point, because that's where the motor is going to run more efficiently. If you get too slow, it's going to overheat. So I'm getting some.
Oh, he's using raw LiDAR data to drive.
Okay, so so they're doing some code,
So we don't have a camera on our robot. It's all
LiDAR data. So something must have hiccuped on the LiDAR, and he's doing some fixing on that. Looks like maybe he has it, because he picked up the control box.
oh, we're moving again.
Moving again. Got it back in. We saw this yesterday where it was going in continual circles. Now the
I wonder if one of the
Right.
tracks is jammed up. We haven't seen that issue as much with this material because it doesn't compress as much, but in NASA's BP1, we were having issues with
yeah
regolith infiltration in the tracks, and
yeah
it just filling up and not being able to get out. And
yeah. This is not our strongest track drive design that we've had,
No.
is it?
not quite. We're using I think it's a K12 chain in there with just riveted on grousers, and every other grouser is bent just like a little bit. It's about a centimeter to help with
it's
traction.
looking like that right track doesn't want
Doesn't want to go.
We had a similar situation in 2011 where we lost a front bogie right after we got our
Yeah.
full load, and we wound up having to dump that load in the mining area, and to our dismay, that pile of material we unloaded looked like one of those big piles right there, and it would have been enough to put us in the top 10 for 40 teams competing, and instead we wound up with nothing because somebody forgot to put Loctite on a screw.
Yep.
And ever since then, what's our motto here?
Well, we,
It's no Loctite.
yeah, no Loctite.
Loctite's not allowed. It either has to be a lock nut, it has to be safety
Yep,
wired,
we
or
use
it has to be some
nylocks.
other type of system that's not going to vibrate or work its way loose.
Yep.
Yeah.
Yeah, we've also had issues in the past with just as we're going down to competition, we just throw it in the back of the van, tie it down, strap it down as much as we can. But in the back of a van, there's a lot of vibration doing a 24-hour trip.
Yep.
So
Yeah.
always have to do maintenance right when we get there to.
So looks
Tighten
like one
everything.
of our big pushes for next year is to figure out on our track systems, figuring out how to keep debris out of there, if that is indeed what the issue is, or making sure we have a more robust motor connection
Yep.
in there.
Yep.
Or maybe we lost the motor due to heat.
Yeah, I believe it's the robot from 2013, Space Ketchup and Mustard. I like their frame design. It's all welded and bent tube, and so it's a completely open system. So if regolith gets in, it's able to get out.
Yeah.
And that's kind of the key when dealing with something that likes to pack in is
Yeah.
if there's any chance it can get in, it will, and it will pack.
Yeah. A little fun fact on those robots. The first year we did the two robots, we called them ketchup and mustard because we were so late getting the design. The seniors that were involved in designing that robot, they said we're in ketchup mode. And then they got to thinking, well, ketchup, but we're doing robots, we should do condiments. So they did ketchup and mustard. Turned out to be the favorite robots at NASA. And they always ask me when we're going to be bringing ketchup and mustard back. And I told them we're not, because we found it was very hard to run two robots in an arena. But the next year then we did space ketchup and space mustard because we wanted to stay with the same thing, but we needed to change it up a little bit on that. But what was unique about that robot that year, we had a very specialized drive in it designed by one of our club members, Nick Hasto, that took a motor from a missile control system that we got donated to. Those are very expensive motors. They were like $4,000 a piece, but they gave us a bunch of them and we weren't going to question it. But it was just the right size that we could package that with Vexpro planetary drives, and they made an in-hub motor, and you can see some of those machinings in the Boyd Lab display window, but also that's the drive that's on Space Mustard.
Yeah.
That's in there too, and it worked very well, but it took a whole lot of engineering and very careful machining to get all of it to work together. That was a very successful drive, but we decided not to continue to use that because if we broke one of those motors, where are we going to buy another one? Because we don't have a budget for it, so we went to something much different in years future. So, but yeah, we've got a lot of history, a lot of different technology you can work off of. You'll stick around as a consultant to the club, will you?
Oh, of course. I'll be on design reviews. I'll be just a text away.
Excellent, because one of the biggest challenge in these competitions, looks like they've killed the run because of technicality of not making any progress after 5 minutes. So we'll see what the results are as far as material collected. It looks like a good amount. It's not going to be enough to catch the top two teams here, but it should be a nice placement for the team nonetheless. So Anna, thank you for your time here.
Yeah, thank you.
And for all your work with the club, and good luck in the future with everything that you do. Stay in touch.
Thank you. Yeah,
Okay.
of course.
All right, so there we go. Cardinal Space Mining Club, Lance 1 has completed its run, and we're going to take a break here for a few minutes while we get the University of Illinois Robotics and Space set up for their run. This is the Collegiate Space Mining Challenge, Iowa State University, hosted by Cardinal Space Mining Club at the Student Innovation Center in Ames, Iowa. Where's my laptop? Okay. Hey, Manny, don't go too far. Now I am. Okay. Well, welcome back. I should say welcome back to myself. We are getting set up here for the University of Illinois Urbana-Champaign team to run their robot in the arena. This will be a bona fide competition run. Sounds like they got their issues sorted out on their robot and they're ready to give it a try. On here, it looks like we got about a minute and a half to go before their competition run will start. We'll see how they do. Just briefly, if you were watching, the Iowa State team, Cardinal Space Mining, ran their Lance 1 in the robot, or ran the robot in the arena. Got a fair amount of material collected, but then they ran into a issue. One of the couplings on the motor drive on the right track, we think, came loose. I'm going to try to get one of the drivers in here a little bit later to talk about some of the challenges they saw in there and some of the sort of things they might do to correct that in the future. But our competition runs are done unless we want to do another demo or something like that. But here again, too, we're not competing. We're just demoing. This competition is for all the other teams here. We just wanted to see how we stack up. And actually, it's been pretty impressive. We've seen a lot of good teams running in here. Though I have to say, I think this is one of the cutest robots that we're going to see running in here in this competition from the, get their team name here that we had. Yeah, the Illinois Robotics in Space. So the IRIS or IRIS, I don't know why I haven't seen that earlier. So IRIS, that's a good name for a happy little robot. That we have here, and we'll see how it does here in just a few more seconds when they go from end of setup to start of the run. And here we go, and we'll see if they've been connected, if they're ready to roll. I don't see anything moving right away, but so I was talking with the team earlier. Their drive system on here is actually a track system from a snowblower. They got it from a used snowblower, about a decade old. Surprisingly light system coming off of an actual product. Most products that we look at for using track drives are quite heavy, overly robust. This seems to be an optimal size for what they're doing. I think the biggest issue, we watched this robot running earlier in the arena, and that we've got motion. That's a very good sign. Here we go. But the biggest issue that we saw here was lack of weight, so lack of traction. being able to move some of the bigger rocks, but hopefully they can get their blade actuated just the right point to be able to move some material into the berm area. I think given the visual delay that they have and what they have for camera view to see, they're being just extra cautious on driving the robot so they don't drive it over a rock or into a wall, because there is a significant second delay. So he's using just little blips of the controls to get it to move. You'll notice here too, just looking at the three views, some of the time delay between the upper right picture and the lower right picture as to what the robot's doing. That lower right picture comes from a camera that you can adjust focus and direction on so that they can see whatever they need to see, and it has a wide angle view that actually becomes a very advantageous camera view to use, as long as you can see what you need to do with your robot running. The right view at the top gives you a good view of the digging area, mining area to pull material from, and the lower left view gives you a very good view of the berm deposit area. So we'll see what their strategy is, what they're looking to do here. He's kind of getting faced up right on that rock. Maybe he's going to try to move that rock first thing. So we'll see what they do here. See what Iris can do. She's got her blade down, ready to give it a push, give it the old college try, so to speak, and see what they can do here with moving this rock into the berm area, because the rock counts just the same as the regolith. If you can get the rock moved into there, that counts as putting volume into the berm area. And as we can see here, the track is slipping. That rock just does not want to go, and they need to be careful here so they don't get themselves buried too deep, too fast, and get hung up on the material, because once you lose traction, that's it. But that's the nice thing about these track drives, is you see, if you disengage from what your load is, usually a track drive will pull you right out, and then you can go to what you need to do with whatever you're going to do with mining. Just an observation here, this robot is very short coupled, just kind of like a Wally robot, and so it does a lot of tilting, and so it becomes kind of a challenge to control your scoop depth as you're running in here. But it is a wonderfully compact, lightweight robot. It does have the camera masked there above the blade so they can see what they're doing as they're driving. You probably have a very good view of where they're going on here. And maybe later I can get one of the club members here to talk a little bit more about their robot and how things are running. During the meantime, we'll just go ahead and watch and see how they do here. It looks like they're going to try to push the second rock. One of the strategies I saw one of the teams apply yesterday was they actually got their scoop underneath the rock and then tried to roll it from where it was at, and just tried to roll it like kicking a can down the road to get it into the berm area. Another method, it looks like they just did, use a little bit of inertia, go in and ram the thing and see if you can't get it to move. But you have to be real careful, because if it bounds up, you could wind up on the rock and hung up, and then you're in real trouble. So that's all part of the challenges of trying to do space mining. And these are very real situations that if we had something up in the moon and we're trying to do things, we'd have to understand that as well. So it's all about understanding optimization and design, optimization of function, mission scope, what you're going to do in here, and have it all worked out ahead of time so you have no surprises in operating the robot. NASA does this on a regular basis. They don't have any guarantee oftentimes of what they're going to run into, and so they have to think of every contingency and plan accordingly. Now they're probably discussing, okay, we couldn't get either rock moved, what are they going to do next? Oh, it looks like they're going to do ramming speed into there, see if that gets any results in getting that rock nudged. Certainly moving a lot of material with their tracks, but looks like no success. That rock is just not cooperating. Now it looks like they're going into shoving up material, getting a good dig going. So we'll let them go ahead and dig here a while and see if they just pray they don't dig themselves into a hole. But they seem to have plenty of traction with that track system. It's certainly a cute little robot. Certainly a happy one. They have a happy face drawn on it, and I'm hopeful that they can get some good results out of that. I certainly think, given that track size that they have on there, that they could easily fit 2 of those on each side of the robot and have an articulated body for turning it. And with a little more weight on that robot, they would have plenty of traction power to push something like that rock. And with a little optimization on the blade design, I was talking with a couple of our cat guys that are here with Caterpillar. They said that the blade could use some optimization, and it could use some wings on it to make sure that the material stays in front of the blade and doesn't get lost around the side of the blade. But those Caterpillar tractors, they have a lot more horsepower than what we're dealing with here. Most of these robots are running on motors that put out anywhere from 150 to 500 watts of power, maybe 600 at the largest. I do know that some of the hobby motors we've used in the past have been as high as 4,000 watts, but those motors run at extremely high speed, so you got to have a big reduction in drive, and they can tend to pull a lot of current. And they have to run at very high voltages, and it's all about power. When you're working in space, you got to have batteries that you have to charge, and you don't want to be expending power at too high a rate. And so, for instance, in a lot of the NASA systems, they have very high speed, low current draw motors, so that they don't have to use a whole lot of power in order to move their robot. And they don't move quickly, they move very slow. That's excellent example is Curiosity and Perseverance. They can go a lot of distance, but they don't go at anything over like maybe 1 mile an hour. It's a very cautious speed and very deliberate the lack of movement, because for instance on Mars on a good day they might be able to get a signal up there to the planet in 20 minutes, but then they have to wait 20 minutes for the telemetry to come back to tell them what the robot did, and a lot can happen in 40 minutes when you think about driving the robot forward. So they do a lot of scouting, take a look at the environment around them, make a determination as to what they're going to do, write a program, send it up to the robot as a packet command, and then hit execute and wait 40 minutes and see what happened to the robot when they get information back. Actually, it's a little longer than that, because they got to let the robot do its job, and then it has to send information back, and then you find out, okay, what did it do? We can certainly see some hand gestures in the control room. They're probably discussing what it is that they should try to do with getting material moved. It might be a good idea to work a little closer to the deposit area and get material pushed in that way. So they're rethinking some strategy, looks like. Okay. Like maybe they're going to try to get underneath this other rock. Oh, repositioning themselves. I'll have to see if I can get one of the UIUC control teams in here after this run. Maybe they can give us a download as to what it was that they did, or what sort of the challenges they were seeing in operating the robot in this arena. Okay, they're right up against one of the obstacle rocks. Okay, good. They pulled away from that. It's University of Illinois, Urbana-Champaign. the Iris robot running in the arena trying to push a rock. We're 10 minutes into a 30-minute run, but I see I got somebody here I would like to talk to. So while we got the run going, since I don't have any of the UIUC students here, Dr. Oliver, if you'd like to come on over, and we'll get you in here. And I'll see if I can get my crew here. Hey, can you give me a camera shot here?
Well, I don't want to interrupt you.
Oh, we'll be okay.
Fighting Illini.
Yeah, no, they're fine. They're
Okay.
fine. Yeah, this has been exciting. Thank you for coming here this afternoon to talk with us and for allowing us to use your facility for this competition.
It's a fantastic event, and couldn't be happier with how it's going.
Yeah,
Yeah,
us
yeah,
as well. We
yeah.
just had Provost Keith here a little bit, and
Excellent.
Associate Dean Hargrave gave him a
Uh-huh.
tour of everything,
Good.
and talked with Dr. Keith for a little bit.
Uh-huh.
He's certainly thrilled to see what we have going here, and
Good, good.
we're very happy with how things are running right now, except for Iris here, who's being challenged by the size of a rock. I feel kind of bad for him, but darn, it's a cute little robot.
It is. It's a big rock, too. So,
Yeah, it is a big
it's
rock.
quite a challenge.
We tried to move it earlier too with our robot, and then I think we paid for it because we had a drive connection on one of the tracks come loose later.
Oh, yeah.
So it cut our run short, but we managed to get some good amount of material dumped in the berm area
Yeah,
before we
good.
did that.
Good, good. So the challenge is multifaceted navigation, some mining, and some excavation, it looks like, with that rock.
Yeah, well, the idea is to go from the start area, navigate to the obstacle area, which
Yeah.
usually should have a crater in it, but we decided to negate the craters, keep it simple for the teams
Yeah,
here,
yeah.
because we have a couple rookie teams.
Uh-huh.
First time ever doing this.
Uh-huh.
And this particular team, they lost all of their experience.
Oh, dear.
Everybody graduated, so they're essentially starting over. So it's
Okay.
like having a rookie team.
Uh-huh. Uh-huh.
They've been in the competition many years,
Sure.
but they don't have anybody that knows what was done in the past. So
Uh-huh.
they came up with this neat little design. I talked with them yesterday.
Yeah.
Their track drive is actually off of a snowblower.
Huh.
They
Okay.
found
Yeah.
an old snowblower, thought, hey, that looks
Yeah.
pretty cool. Let's use that.
Yeah.
Uh, and so it's a unique little design. It's a very lightweight robot too, but
Uh-huh.
as you can see, that creates a problem for having enough oomph
Yep.
to move a rock.
Yep.
So
Oh, that's great. That's great.
yeah,
Well,
but it's
I'm-
fun to watch.
Yeah, and Cardinal Space Mining has been amazing to see the success over the last few years, and this engagement is just a testament to your, ambition and success. Jim, when this place was coming alive,
Yeah.
I said all these clubs that have access to the resources here better be top 10 in the next few years, and yours was the first one to make it a reality.
Yeah.
In Lunabotics 23 and tied for first in 24, and then our solar car team, Eliana of the Prism team, came in third this year,
Excellent.
racing from Kentucky to Wyoming.
I didn't get a chance to hear that.
yep.
That's wonderful news. Yeah.
And most recently, the SAE Formula team came back from Michigan with 5th place overall. Amazing
Wow.
competition. Their aero kit was they all done in the composite shop here, and they were competing against teams from not just the U.S., but in Europe and South America. Some of those teams really heavily supported by companies like Porsche and others.
Yeah.
And our teams here in the middle of Iowa and came in 5th overall, which is
That's impressive.
so it's really coming true. It's so exciting to see the energy that the students bring to these clubs, and the benefit for them to learn how to solve problems on the fly and work as a
Absolutely.
team. It's some really great skill development in these clubs, and certainly Cardinal Space Mining is just really up there. I always say it's not just the facilities. It's faculty mentorship of people like you, Jim, to just get
Well,
them
and you
fired
too.
up.
You recall
Well-
when I started here, you and I worked together on totally revamping the sophomore
Yeah,
design
we
class.
did. We did some good work along
Yeah.
when we both had darker hair, I think.
Yeah.
But
Well, I had a
yeah.
lot more of it than I do now. Yeah. Thanks to these guys.
No, it's great. Our program is really going strong, and all the mechatronics associated with us is it's exactly the kinds of things that there's no machine that runs with a single technology, right? And
Not
so they give us
anymore.
some computers, some mixed
Yeah.
circuits, hydraulics, all kinds of different things. And I noticed you got the SICK sensor on the front, which is
Yep.
fantastic use of technology.
In fact, our run that we just did, he drove it totally on the LiDAR.
wonderful.
Didn't use a camera, used the LiDAR
That's a great.
to drive it. That's pretty
yeah,
impressive.
That's excellent. Yeah.
That's prepping for doing autonomous operation, kind
Absolutely.
of saying, could they
Yeah.
ascertain is exactly where they are? And
Yeah.
it worked pretty good until the track drive broke.
Yeah, that happens. That
Yeah,
happens.
it's just the way it goes in these
Yeah.
sorts of things. So.
Excellent. Oh,
But-
that's exciting. And then, so tomorrow is the final competition?
Yeah, tomorrow will be the final run of
Okay.
competitions. We'll have our banquet at the Memorial Union in the
Nice.
Great Hall tomorrow
Okay.
and give these wonderful trophies away.
Oh,
like what
wonderful.
I
Yeah.
had. This was designed by one of our team members, Mason Eck. He
Nice.
bought the orbs, which is a laser
Nice.
image of the moon in there.
Yeah.
And then he
Yeah.
water jetted aluminum plate in
Very nice.
ag engineering.
Yeah.
And then 3D printed the rest of the pieces himself, bought the driver board for all the optics
Oh, very
that he
nice.
put in there. And it's going to sit on a lovely wood base that'll have the plaque on it, the first, second, and third place teams in
Nice.
this competition.
Oh, that's
But this
wonderful.
one we get to keep.
Oh, good. Okay.
So we can put it in our trophy case
Yeah,
for
yeah.
hosting this
That's great.
event. And it'll have the plaque will have the CoSMiC logo on
Sure,
it.
sure.
And it'll be something we can look at and fondly remember what we did here
Excellent.
this week with bringing these 11 other teams from across the country. We got them here from San Diego, California,
Yeah.
all the way to Boston,
Yep,
Massachusetts.
Yeah,
that's-
Virginia, New Mexico,
Yep.
all over the place. It's impressive. The commitment by the students all over to really want to come here and compete. And I'd love to have this and continue to improve our lunar testing facility in the building here. And I'm all for that idea,
Yeah.
Jim, and project. Help to support it and continue to grow our presence as
Yeah.
space mining leaders. It would be fantastic to have.
Really good. I understand Vermeer made an announcement a few days ago
Yeah.
about their space
I
mining.
saw that. Yes.
Yeah.
Yeah, that's cool.
Well, that
Yep.
means I'm going to have to call Mr. Indringa and
Yep.
hit him up for some sponsorship on
go.
expanding this lunar
There you go.
test facility we
That-
have.
Perfect timing, right?
Yeah,
Because they're
yeah.
getting some great press. No,
Yeah,
that's
you know,
fantastic.
it's like the old cowboy adage goes, timing has a lot to do with the outcome of a rain dance.
That's exactly right. Well, that'd be great. With this, our temporary pit here was another miracle of amazing, pulling it together, but it's
Well,
working great. And,
Yeah, it's all about innovation. I
Yeah.
have to say our students have been very innovative.
Yeah.
They catted this all up on SolidWorks
Yeah.
and figured out what their build list had to be,
Yep.
ordered it, got
Yep.
it in, put
Yep.
it together,
Yep.
got all of the approvals for
Yep.
building a temporary shelter
Yep.
inside a shelter. University staff
Everybody.
kind of frowns on that when
Yep.
the students are doing something like that, but we got approval to do it
Yeah.
nonetheless, and they did a fine
They
job
sure
of it.
did. They sure did. It's working great.
The other really impressive thing, facility said, well, it might take us an hour or two to get that material in there. And when it got here, they got going, they brought an extra skid steer. They had that loaded in there in 10 minutes.
That's fantastic.
That's,
Yep.
that's unbelievable.
And smooth it out and off you go. You spinning again.
Yeah.
Oh, that's awesome. Well, good luck, Jim. Really
Yeah.
a pleasure to chit chat with you a little bit. And,
Yeah.
so proud of you and your team and what you've been able to pull off here.
Well,
This is
again, I want to
fantastic.
thank you so much for being the director of the Student Innovation Center and all you do for making this a fantastic place for students to innovate,
Excellent.
create,
Yep.
and do the sorts of things that they do, but more importantly, gain the hands-on education that they need to be
Exactly.
better engineers.
Absolutely.
Is really important to all of us
Absolutely.
here.
Cool.
Okay.
All right. Have fun, guys.
Okay.
And good
Thank
luck,
you.
students. Keep up the good work over there. We'll see you guys.
All right.
Yep.
Thank you, Jim. That was Dr. Jim Oliver, director of the Student Innovation Center here at Iowa State University in Ames, Iowa. And a fantastic support from him for us doing this here at the Student Innovation Center. So we've got, Iris just moved a rock. She's been working a long time at it. She's still got 10 minutes to do that. Maybe she can keep that rock going and get that into the berm area. It's coming into view in the other picture. Oh, this is exciting. Oh, she's going to put the shovel down. Going to do another large impact into that to get that to move. Some wonderful views here. Oh, get it lined up. He's struggling a little bit with the lag in time between what he sees and what the robot actually does. Oh, there he went too far. And this is where driver training comes into play, because you got to understand how far do you move the control for how long in order to get a certain length or rotation of movement on the robot, and it's called time of flight. And obviously, we've got a driver here that needs a little more training on that area, but they actually have been doing a very good job in here of getting this far on things. And even if they have their own camera on it, it's got to go through all of the Wi-Fi and distance of cable. And so there's about a 2.5-second delay between what you see on the screen and what's happening at the robot. And the robot moves first, and then you see it, and then you have to think about, okay, what am I going to do next? You can't be guaranteed that just because you push the stick forward to drive the robot straight forward, that it is indeed going to drive straight forward. Sometimes they skew a little bit to the left or a little bit to the right, and then all of a sudden you're in trouble. So they have to be very careful what they're doing and making some headway here, getting that rock in there. It's really important to them that they at least get some volume in the berm area, and a rock counts for a lot if you can get it in there just because of their sheer volume. But if you have a problem moving it, it takes a lot of effort and a lot of power, and they will be judged on power usage as well. That's one of the key things that we track here. So the way the scoring works, my understanding, and I'll get clarification from my students later. First, they go through tech inspection. If everything passes techs, they get a X amount of points. And then there's a deduction for weight, 10 points for every kilogram the robot weighs up to 80 kilograms. And then there's points for communication, deduction, communication bandwidth used, deductions for power usage. There is a watts counter on there that keeps track of the watts hour that the robot expends while running. And we check that at the beginning and end of every run and take a measure as to how much watts hour that robot is used in doing its operation. Then, of course, there's the regolith excavated and deposited in the berm area as to what they have for volume when they get done. So far, the max volume we've seen collected, 181.5 liters by the Miner 49ers out of New Mexico Institute of Technology, followed by San Diego State University Team Creed with 147.4 liters. However, because of how the runs are scored, San Diego State was in first place after the first run, and New Mexico Tech is in second place. Third place, Youngstown State University, 428 points. And now that we've got some teams starting to do their second run, hope to get some points from that. We'll get that updated as to what they have. Well, they got Team Iris here has got another 6.5 minutes to get that rock nudged into the berm area. So we'll see if they can successfully do that as they're moving this very cute little robot in the arena. It reminds me very much of Wall-E or Mo or one of the other characters from the Pixar movie. Very solid little design, though. It moves very well in the regolith and has not seemed to have any problems as far as overtaxing any of the mechanical systems. There have been no bending of anything, no deformations. It's just a simple case of physics, weight and traction, and how that plays together with getting work done. And he's been over that rock several times, or she, whatever you want to refer to it, and has not been stuck yet. That's very impressive in itself, what they're doing here with this robot. So hopefully they'll get that scooped down a little bit more, roll that rock in there. We still got 5.5 minutes to do that. Sometimes the blade gets in too deep and they don't have enough traction with the amount of material they're trying to move. That's one of the challenges here. This material, the deeper you go into it, the higher the shear stress required to move that. That basically equates to length of shovel and the shear stress required to get the material to move, and that winds up being pounds of force or newtons of force in here. As I use these different terms, for those not familiar with what, if we're familiar with pounds force, then there's a question of kilograms force versus newtons force. And by comparison, 1 kilogram force is going to be 2.2 pounds of force. And by comparison, 1 pound of force is going to be 4.45 newtons. And if you look at kilograms to newton, that's 9.81. These are all different units that we have to use in engineering, understand the difference between those. And then that's just force. You want to get into mass and into length, at least the one constant that is universal throughout the world, and that is time. Seconds, hours, minutes. So though I'm pretty sure spaceflight has another time element involved with it that I haven't been privy to learn. But given that, we got 4 minutes approximately left for Iris here to get that rock put into place. Hopefully the drivers for University of Illinois can get that accomplished. Trying to work off the corner of the shovel rather than off of the main blade. They're getting pretty close to the edge of that wall, but if they can get that in there, into place, they should be able to make it. Well, it looks like they're going to get underneath it and give it another big push with the tracks. Maybe you could pick that scoop up a little bit. Maybe you could roll that rock a little bit more. There he goes. And it looks like success. Give her one more nudge there, guys. Get her all the way in there. One more time. There we go. All right. Excellent. Congrats. That gives them at least some volume to work off of. Given the lightweight of the robot, they should have a good score coming out of this. We'll see how that plays out for them. With a minute and 45 seconds left, maybe they can get a little more material in there and increase their score just a little bit further. There we go. A little more material in there. That'll help. 30 seconds to go. Maybe you can get one more shove on a Burma material and get it in there. 20 seconds left to go. $13, 9, 8, 7, 6, 5, 4, 3, 2, 1. And now they got back the robot out there because we can't measure the volume of the robot, guys. You got to get your robot backed out of there to get the berm count. Nice try. But there we go. University of Illinois, Urbana-Champaign, Iris. Good job. They're being commended in the fact that they have a robust robot from the standpoint they abused it very heavily out there, and it's still running. Okay, looks like next up that we're going to have, and it's going to be the University of Arkansas Razorbots will be coming in with their robot to do their next run. Again, this is the Collegiate Space Mining Challenge coming to you from Iowa State University and the Student Innovation Center in Ames, Iowa. All right, thank you. Okay, so we've got University of Arkansas Razorbots are getting loaded up in the arena here to make their, is it this second run or first run? Second run. Yeah, we'll see how they do. They have an interesting little design. Maneuvers very nicely, but it's a case of weight and digging power with the scoop last time they ran, and they did have some technical issues. But they were able to do a fairly decent run as far as points, but they didn't get much material because of the technical issues they had. So hopefully this time they'll have it sorted out. They'll get a fair amount of material, and we'll see how they do. So we got about 3.5 minutes here before they're ready to run, and we'll keep a close eye here. Oh, I see what he said. At our trophy here, they brought the base in, and it's got a magnetic capture on the base that keeps the trophy on the base, and really beautiful trophy designed and built by Mason Eck, one of our club members. Very creative design, very appropriate to the moon mining missions that we do, and we're really looking forward to sharing this award with the top 3 teams that win here at the Collegiate Space Mining Competition. Of course, special thanks to our sponsors, Caterpillar, Collins Aerospace, Danfoss, SICK, Sensor Intelligence, MEC9, Iowa Space Grant Consortium, and the Iowa State College of Engineering. Some of the things they have to be careful with here, making sure they get things hooked up, is everything on? Is their emergency stop switch rotated so that it is not engaged, because that shorts out the battery to the motors and controllers and essentially kills the robot. And those things usually are engaged when the robot's taken out, so there's no danger of the robot running on somebody while they're handling it manually. But then you got to remember to turn that off when you bring the robot into the arena to get ready for the next run. So they're smoothing out the work area here, getting all the material nice and loosened up after the previous run. They've put the pitchfork in there to get the subterranean material loosened up. The stuff compacts down pretty good. We had one of the other teams working in here earlier, and they had a system. We didn't plan for people digging deep, but the team that was running in there, I believe it was University of Minnesota, had their robot designed to dig deep, and they went to dig deep, and the material got so dense that they couldn't get their digger system to go any deeper. So we apologize for that, but hopefully with a little adjustment and strategy, maybe Minnesota can adapt to that and get a good second run. So I'm just going to take a look here. So the University of Minnesota, they collected 33 liters of material in their first run, and too bad. And see what their score was. Their total score on that run was 325 on their first run on day 2. Go back here and take a look. We got our Cardinal Space Mining second run. See how we did there. Okay, we collected looks like we did 72.5 liters. Some better than our first run, but still not enough. We actually had another technical failure. One of our drive systems came loose on the right track, and it stopped responding. but we did get a score on the second run, almost doubled our score at 435 points because of autonomous operations and dust-free operation and amount of material collected. So not bad. Still not enough to catch the top teams though. San Diego State University, Creed, still stands at the top at 852 points. The New Mexico Institute of Technology Minor 49ers at 767 points after the first run, followed by now Youngstown State at 428 points and University of Minnesota at 325 points. So it'll be interesting to see here if Arkansas can better their score of 262 and bring themselves up on the standings. So here we go, start of the run. Let's see if they can get rolling here, and look forward to seeing if Grace and team can get the robot to respond to their commands and do the things that it's capable of doing. They certainly have a nice design, very clean looking robot with a nice wheel design to it. Very interesting bucket design as well, kind of a combination of a blade and a scoop, and we'll see how they do. Looks like we're having some communication issues. Jacob is coming in there. Jacob Mosier, one of our controls leads, is doing some adjustment on the computer. Hey, Mason. almost 2 minutes into the competition run for the Razor bots, and still no activity out of the robot. So obviously connection is a challenge. I see there in mission control, Jacob's overlooking what they're doing, so he's helping them kind of sort out what they're having for connection woes. We don't never have a full guarantee that things are going to work. We do the best we can with setting up our part of the internet so that they have an active Wi-Fi signal in there, but depending on what they put in their robot for their equipment and is it compatible with talking with our equipment is always the challenge. Something we'll make a note of in the future is we will understand which sort of combinations of modems have to be there for things to operate properly, and then tell all the teams that they need to bring their proper equipment to work with our proper equipment. And I know NASA does this in their operations, but even then it doesn't guarantee that they're going to get a full connection. And that's one of the more common problems or issues we see at NASA as well when we're running down there, is that we can't get a robot to connect or communicate. So fingers crossed here, we'll see what happens, and hopefully they can get a full connection. They do have the scoop moving, so that's a positive. They got it up. Maybe now they can get the drive motors to go, and they'll be on their way to hopefully having a very successful mining run here at CoSMiC. Again, special thanks to Caterpillar, Collins Aerospace, Danfoss, Six Sensor Systems, Mechdyne Corporation, and Iospacé Grant Consortium, and lastly, Iowa State University College of Engineering for supporting us in doing this. Looks like they're doing some more coding, getting things sorted out as to why things aren't turning on. One of the big challenges when you're using modems is understanding what password has to go in to log into the Wi-Fi. We've certainly seen some teams get challenged by this. We try to keep that up to date, but that does pose some connection issues. And it looks like the operators have changed seats. Somebody's taken over computer A. This is really quite a technical task that these students are doing. They have to learn all sorts of computer programming. They have to learn electronics. They have to learn mechanisms, understanding power conversion, and mechatronics. That's the combination of electrical and mechanical systems. They got to learn about motors. They have to understand motor power levels, motor operation limitations. They have to understand about gears and chains and grousers. Grousers would be the blades that are on a wheel or a track that grip into the ground. You can have too shallow of a grouser, you can have too tall of a grouser and not be able to optimize the traction that you get out of your robot. Grouser material makes a big difference too. We saw earlier the UIUC robot running a snowmobile drive which had rubber grousers on their tracks, but they weren't able to get the traction to get the rocks pushed that they tried. But they did get one eventually into it, but it took almost their full run time to get it in there. Whereas a metal blade grouser would probably a bit into the lunar regolith much more readily and give them quite a bit more depth. We've experienced the same thing. We tried some rubber tracks in the past with our Mars series, our early Mars series, because we wanted to come up with something that didn't take as much work to build. So we purchased some rubber robotics tracks with very good rubber grousers on them, but we found that they just didn't bite into the lunar regolith well at all. And we didn't have the sort of traction that we needed to have to do the things that we do. So we reverted back to PVC belt with PVC belt with metal grousers on it, and have since then graduated away from that to making something a little more space capable that's out of steel chain and aluminum plates with bent grouser plates on there, usually about 3/8 of an inch tall, sometimes a 1/4 inch. That seems to be an optimal height for a grouser to bite into the regolith and get good traction. Here we go. Okay, they got their connection problems fixed. They're now rolling. This is good. Congratulations, Arkansas. This robot moves very nicely over the material. It turns well. It doesn't have a problem with stirring up a lot of material. Very good motion on it. I really like the single boom design on the actuator and scoop. It's just a question of, can they get the right control on the robot to get an optimal cut into the material and pick up that material and get dumped into the berm area. So we'll watch here intently and see how they do. Again, I really like this wheel design. As you look at it, you see some flat panels, and the panels with the grousers on it. They appear to be about 1 centimeter in height, and staggered a little bit as far as left and right, various widths. And the vehicle appears to have very good flotation, very lightweight in the regolith, but we'll see soon here if they're able to get things rolling as far as getting the scoop down and digging up material. They appear to be using a joystick controller. That's usually my preference, one of the aircraft video game type joystick controllers. Usually they have a little better dexterity to them than the Xbox controllers, so that you control how fast, how far you're moving based on the motion of the joystick. But looks like they're having some connection issues because they're really looking there at the computer to see what the computer is saying. Those are always challenges in doing these things, because the robot sometimes will like to disconnect, or a circuit gets overloaded and drops out, and then you have to reconnect to it again. And based on gestures that they're doing in there, they're obviously fairly stressed out at the moment, but keeping their cool, just like a NASA engineer would, and continue to do coding and try to get the thing to do what they need it to do. Hang in there, guys. You can do it. You got about 20 minutes left, so they're a third of the way into their run. First year NASA held this competition, we had 21 teams show up. Iowa State was one of them. And they were going to run a single 15-minute run, and that's how everything was going to get scored. And we went to run that competition, and after one burnt-up robot and several suddenly rapid, unexplained disassemblies, we discovered at the end of a run that nobody had successfully collected any regolith, and NASA was sitting there saying, okay, now what do we do? So they told us we could go ahead and we could fix our robot and have it back in impound the next day. We could be allowed a second run, and all the teams did that. Surprisingly, out of the 21 teams, only 3 teams qualified. Unfortunately, Iowa State wasn't one of them, but we did have a large crowd rooting for us, cheering us on. We had a very nice looking robot, but we learned some of the important lessons of physics of collecting material. We thought it would be really cool, and that's a phrase I always warn my students about. If you're brainstorming and doing engineering ideas and somebody says, hey, wouldn't it be cool if, look out, because that's usually not going to be the best engineering idea you can do. But at any rate, back to the story. We decided to make a raised hopper because we had to dump our material into a receiver that was a meter above the ground level. And we wanted to use a conveyor to get it up there, so we used a bucket ladder for that. But we wanted to keep the material up there so our bucket ladder could be as short as possible. So we created an elevated hopper, and we got thinking, how are we going to get the material in there? So we decided to use an auger and an impeller and a blow chute, just like you do with a snowblower, figuring that in space, even though we have no air, the auger would still collect the lunar material, the impeller would still impact the material, and uses centrifugal acceleration to accelerate the material and have it fling off the edge of the impeller blade up through the chute and into the hopper. And because of the nature of what it was, if we wanted to lose the heavy rock or anything that was not important to us, that would drop out the open chute. Well, what we had not planned on was that we are operating in an Earth atmosphere. And as the robot was clawing up material and impelling it to go up into the hopper, it was also grabbing the air. And it wound up pressurizing the hopper because the hopper was sealed. We didn't want any regolith escaping out of it. And so with that, as we were trying to get regolith up into the hopper, it just blew it all out again. And we wound up collecting something like 3 half-inch size rocks off of the surface of the lunar pit. And that was it. And that was our second run. And so we weren't successful. The next year, we took care of that problem. And we had a very successful run from the standpoint of collecting material. But unfortunately, one of our bogies on one of our track systems came loose, and we couldn't return back to the deposit area, and we had to dump our load right there in the mining area. And we had enough material we could have placed in the top 10. So that was a lesson learned, and we went on to make some very nice designs after that, getting away from that snowblower auger design and going with bucket ladders and blades and track systems, and making sure that under no circumstances were we using a bolt into the end of a shaft that was being secured by Loctite. Everything from then on had to be a lock nut, or it had to be safety wired. So still no activity out of the Razorbot here as we're watching to see what they can get going. Most unfortunate. It's very frustrating to get here, do all this work, have the robot work a little bit, and then have it drop out and see that it's coding issues or something to do with the internet. And these are all things that teams have to sort out. Halfway through the run now, still nothing collected. Fingers crossed. Hopefully you can get a report from them later to see what their struggles were. It's important information for all of us to know so that we can make the second time we do this, if there is a second time, to make it better than the first. Again, the reason Iowa State or Cardinal Space Mining Club is doing this is to give an opportunity for those teams that did not get a chance to travel to the Kennedy Space Center and compete to have an opportunity to build, test, and compete with a robot here at Iowa State and win some prize money and a trophy to take home for their efforts. And so we are very appreciative of the teams that said yes to want to come to this event, and very appreciative of the university allowing us the opportunity to hold it. And hopefully you're enjoying watching this run. I know it's not always as exciting as we like it to be, but that is space and space technology and robotics. It's a whole lot of waiting for something to happen, and then all of a sudden something does happen. It kind of catches you unaware. So we'll take a look. I can see we got by our stream 48 people watching, so thank you out there who's tuning in on this to see what we're doing. So kind of our standing rule is if you hit 5 minutes of runtime with nothing happening and you're not making any progress either through coding or through motion of the robot, then the run will be canceled. They're coming up pretty close on that time now. Well, a little movement out of the shovel, so they're getting something going on the robot, but oh, we got some more activity. Here we go. Maybe they got a connection going now. Okay, so they got some material into the berm area by doing a little blading. They got their scoop down. That's a positive sign. Digging in here a little bit, trying to move more material. Like I said, this material gets pacted very easily, and then it gets very difficult to cut into. That's one of the challenges in using crushed lime rock compared to some of the other materials that NASA and others have used to simulate mining on the moon. But we'll continue to watch and see what they do. So at least they got some activity going. They'll get a little something out of this run. They had similar technical difficulties last run where they it lost a lot of time getting connections squared away. Once they finally did get running, they weren't able to get much regolith collected. Oh, big effort pushing. They're going for broke here. Pick their scoop up, take what you have in there and dump it before you get stuck. One of the big dangers is you get that scoop in there so hard that you can't get it picked up. All good, they got out, but they left their material behind. Five minutes left. Get your scoop position where you think it should be, and then you move and you get in out of a rut, and the next thing you know, your scoop's not where you want it to be. Okay, that's good. Stop, pick your scoop up. Don't back up. Oh, they lost their load. Something tells me their scoop rotation isn't strong enough to rotate out of that. And that's becoming a problem for them. Maybe they killed the motor. Because I don't see much rotation coming from the scoop. Well, it looks like they're going for an all-out affair for, oh, hey, they got some material in the scoop. Pick it up, don't lose it all. Yeah, it looks like their scoop tilt motor has died, because otherwise they would have dumped that material there that they had. I think that gesture just said it all. frustration. Down to a minute and a half. Ooh, very good. They got the bring the scoop up. Now maybe they can just get it over there and dump it in. Don't back up. Go. Oh, wait a minute. That's motion out of the scoop. Okay. Not quite understanding what's going on here. Okay, drive it forward, dump it in. Don't back up. "30 seconds left, guys. Make it work. Make it work. Get in there. There we go. Now dump it. No, not too far. Stop." Obviously, they're having a problem between what they're seeing and what they're doing. Most unfortunate. 8 seconds left. Don't think they're going to be able to do much. And they're done. Okay, well, that's Arkansas University of Arkansas Razorbots second run. And they're going to back the robot out of the way so that they can get a measurement on their berm. Unfortunately, they left more material in their scoop than what they have in the berm area. Most unfortunate. So hopefully get a chance to talk with them and find out what the challenges were that they were seeing, and maybe we can help them with figuring out what to do in the future. Okay, up next looks like it's going to be North Dakota State University Bisons with their run. Hopefully we'll get somebody to talk to when they come and make their run. Hey, looks like we have North Dakota State University Bison Robotics setting up for what looks to be a test run. I'm getting shrugs from the audience that's sitting there. Any of you with the team? No? But nonetheless, very interesting robot design. Looks like it could be easily used as a robot or a dining table. Sorry, I don't mean to make fun of the robot. That actually could work very well. But we see all sorts of configurations in the space mining robots. And some work really well, some don't. But you never know for sure until you see it actually run. And that's the fun thing about this. There's not one cookie cutter design that just works really well for everything. And then there's everything else that goes into it. I did have a chance to double check with a team that just ran University of Arkansas Razorbot. And there was a valuable lesson to be learned out of that run, and that is standardized wiring design and having a full wiring diagram and sticking to the standards of your wiring diagram when you work on the robot. Apparently they had to do some motor work overnight, and somebody got one of the motors wired backwards, and they spent 20 minutes going through the code until they could get all the motors working again. And then once they got that done, the camera dropped out that they had on the robot that had a 2-second delay, and they had to wind up using a camera that had a 30-second delay. There's nothing harder than driving a robot where you do an action, you have to wait 30 seconds to see what it did. That becomes impossible driving conditions. So a little lesson for all of us to learn. Get a good wire harness design put together for your robot, standardize all the connections, and stay with that so that you don't have any issues. Make sure your wiring is all protected in running sleeves so that grounding doesn't become an issue, because they were chasing one of those last night. It took them hours until they found where their short was at. That was causing them grief on the operation of their robot. And these are some of the many challenges we run into in building these robots. So it looks like a practice run. They have the robot set up in the, not in the start area, but in the mining area. So I would say it's not a competition run. Their team is still standing there while the time is counting down for the setup. Comes a couple more people, check in on things. Well, cameo time must be a practice run because they're burning up their competition time if they're making a comp run. Now, based on my history with this team, and I've competed with them a lot over the years, this is a significant departure from previous year designs that we've seen from them. They've had some very traditional type design robots. I've seen them use a bucket drum and bucket ladders, but to have a bucket ladder conveyor hopper all in one type thing is fairly unique, and it will be interesting to see how this works out for them. Oh, come on. teams down in the lunar pit. I'll let you know there is a special flavor ice cream available at the Sparks Cafe on the 4th floor of the Student Innovation Center. I just got a sample given to me to try, and it's really good. You're gonna have to try it out yourself. It's called Lunar Lavender. So yeah, and it's as luxurious as it sounds. So it's got honey in it, whole milk cream, very low calorie, I'm sure, but it's very good. It does contain milk, so if you're lactose intolerant, I'm sorry, but it is oh so good. So if you're a little hungry, and I think they're still open for 15 minutes, you might run up to Sparks Cafe and see if you can get you a cup of Lunar Lavender ice cream. for those watching online, it appears that this is a test setup that they're trying to do. And we're having issues with connection here for NDSU with what they're trying to do. So we'll just continue to watch here and see if they can get this sorted out on their robot. just talking about your scoop system over there, how it rocked and was doing a good job. So hopefully you can do it again. Yeah. Oh. Okay, and we're moving. And we're already in the mining area, and we'll see what, oh boy. Are you guys running any autonomy on this run? Oh, oh, oh. You poked a hole in my plastic. How dare you poke a hole in my plastic? Okay, second chance here. Hey, that works. That works. If it gets there, it gets there. You need to talk to that student about the finer art of driving. We were just talking about one of the other of my favorite drivers was from the University of Australia at Sydney. And they had a robot very similar to, oh, he's going after my wall again. Very similar to New Mexico Tech's bucket ladder and the conveyor, but he had the whole time of flight thing down pat. And he didn't have to rely on the picture on the computer. He just knew where it was at all times. And he would come crashing up to the wall where a receiver is and immediately hit the discharge button. And that material would come flying out of there in a mountain into the receiver and disappear. And he would be gone in a flash back out to the mining area. And he collected a lot of material, but the robot weighed 79.5 kilograms. So the penalty points on weight couldn't overcome the points that we got on autonomy points and on robot weight because we were 35. And with 115 kilograms, we won the mining award and the Joe Cosmo award that year. So, but I was still very duly impressed with that robot. I thought if anybody could come up with a lightweight version of what they had created, it would rock. So, but I have to say, this design here is rocking pretty good too. How much again? Yeah. Yeah, actuator speed makes all the difference in the world. As long as you have the power too, because oftentimes you get them faster than the forces available go down. So it's Well, gee whiz, it's only 4 minutes in the run. You got the whole backside of the berm area now covered with material. What are you going to do when you run out of material in front of the berm area? Shouldn't you try the farther place first and then go to the nearer place? Oh, not too far. Oh, It's getting sight out of the boundary, but some tell me that's not going to be a problem, though. You know, some of these short coupled robots, it was fun to watch them run because just about the time they'd get their scoop or their blade just where they thought it was and they move the robot, it hits a different slant. Now all of a sudden it's too deep or too shallow or not engaged at all. And so anybody from your team want to come and talk about what changes you made? Ah, you drew the short straw again, didn't you?
Somebody new to do it. You guys already see
Yeah, yeah, they're all chicken. So, Skylar, what's the difference on this run from last run? And last run was a pretty good run.
Yes, so this run we're trying to optimize where we're placing our material.
Okay.
As you can see, we're placing it more to the back this time so we could get more in the berm.
Yeah.
Last year, I ran into the trouble where it was so high, it would reach the top of our bucket and we could end up.
Well, right now you've got a fair amount of material that's not going to get scored because it's past the back
Yeah.
line. But nonetheless, looking at that, what we recorded, you know, you might do just fine because you had the most material collected on the first run at 181 liters.
Yes,
followed
and
by
that included 10 minutes of that run. We were having connection issues, so we
Yeah.
only got 20 minutes this time. We've gotten the full 30 so far.
Yeah, well, knock on wood.
Yeah, knock on wood.
Not through the 30 minutes yet.
Yes.
So, but yeah, and San Diego State had 147.4 liters. You had 181.5. Your two teams are clearly collecting the most material out of anybody so far. It's very impressive. Our second run there, we got 72.5 liters before our track drive came uncoupled.
Oh,
That's what
That's unfortunate,
stopped
yeah.
that. Yeah, but that robot's been run a lot, and yeah, it's getting kind of tired.
yeah.
So
Robots do get tired
they
easily.
do get motors wear out, gearboxes wear out, set screws shred, you know, and such. So
Uh-huh.
you know. Okay. I think Caterpillar would be duly impressed with the remote operation of this robot compared to their skid steers that they've been running at the NASA competition. They were having all sorts of connection issues, and it appears here that you've got yours pretty well solved. Whoa! Okay, you're pulling over, bud. We're checking you for DUI. Now, I just want to make it clear as far as scoring, you do not get points for creating a negative elevation in front of the berm. We only get counted for the height of the berm based on the natural plateau that we started with. That is, we can even figure out where the berm areas is by the time it gets done.
Yeah.
My goodness, this is incredible. That is the very nice actuator speed. Oh boy. Those wheels really do claw at the
Yeah. So
ground.
last year we did Terra Mechanics on it.
Yeah.
And, they proved to be really effective, so we stuck with them and didn't want to change them.
Yeah. If it ain't broke, don't fix it, right?
Exactly.
Yeah. Or there's a great old cowboy life adage that works very well here. If it doesn't seem like it's worth the effort, it probably ain't. That effort being changing the design of the
exactly.
wheels. There were, hey, and we got a guest come rolling in over here. Hey, John, if the track's not rolling, you might get check the set screws on the sprockets in the track drive, because the one might be loose if it's not wanting to turn on you. I have a feeling when we get done this run that the pit crew
This is
and the
gonna be-
box is not going to like your team.
That's a good thing, isn't it?
Yeah, it's a very good thing. It's a very good thing. They're going to have a lot of scooping and
Yeah.
shoveling to do when you get done here. They may ask you just to keep your robot in there and put it all back. I think it'd be a lot easier. That is getting to be a pretty deep hole. Pretty soon we're not going to be able to see your robot. Whoa, 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 whoa. I don't want to see him go over backwards. If that bucket load gets over that control box,
Yep.
it's over. I have to ask your driver, does he work for a construction company? Real skid steer? Okay. Okay. That's, I wouldn't say that's cheating, but that is having a plant in the team. Yeah, you can tell by the way that everything is going so fluid here, and he
Yeah. We've had about
jogs that bucket.
we've had about 15 hours of test time with the robot in our
Yeah,
arena at
Yeah.
our university. So it's had a lot of practice.
driver training is so critical in these things.
Yeah.
Knowing your machine. Or one of my favorite quotes from an old Air Combat, they had Chuck Yeager quoted, "Remember, it's the man, not the machine." This is an impressive pile of material once again. And we're still not even halfway done. Looks like he's taking a break. Robot must be winded. And here we go again. Oop. This is very entertaining. I'm sorry, audience out there, I'm not saying much because I am just mesmerized by the action of this robot. This is, we're all watching here, and
Yeah.
eager anticipation as to how big this mountain is going to get that we have in front of us. You are really laying the gauntlet down. I hope Eric Reiners is watching. This is very impressive. So have you ever interviewed with Caterpillar, or has he ever interviewed with Caterpillar?
I don't know.
I might want to consider doing that. He's really got this teleoperations thing down well. Now, in the operation of this, are you using your own camera on the robot for
Yes, we're
seeing what
using our
you're
own cameras, so we're not using any of the cameras that are in the
in the
right now,
arena? Oh, so he's driving off that camera right on the
just on
nose.
the robot.
Wow, that's even doubly impressive. So how many cameras do you have on the robot? 4? 3?
3 cameras on the robot.
Where are they positioned?
So we have one,
I see the one right above the bucket there.
and then there's one, you can see it in yellow right there
Oh,
in between
yeah.
the 2 wheels.
Yeah.
And then there's a backup camera in the back, so he knows how far to back up.
Oh, perfect. See, and that's just what Caterpillar does a lot on theirs, but I have them side cameras so you can see what's to
Yeah.
the side of you. But one of my favorite lines from an old movie called Cannonball Run, one of the drivers says, rips the rearview mirror off his car and says, "What's behind me does not matter." But I don't think that's the case here.
Yeah.
Okay, well, you've more than covered the berm area here, so you better start considering how you're going to create a ramp to get up to the top of that mountain.
Yeah. Like, there he goes. He's trying to create a nice little ramp right there.
Oh boy. Now that is, I don't know if that's stupidity or bravery or a combination of both. Wow. He's going to push it on up. Because you got to be very careful to make that too steep. He'll roll it right over backwards. But I think he knows exactly what he's doing. Well, there you go. There you go. You know, there's an old adage in the Cowboy Guide to Life, too, that says when you find yourself in a hole, first thing you need to do, stop digging. He's got quite a hole going there. Hope he doesn't roll that over on its side. Do you have any self-righting mechanisms on this?
What was that? Self-righting?
Self-righting mechanism. He rolls it over on its side. Of course, at this point, I don't know if that's a huge issue.
Yeah.
Wow. No, at the risk of sounding a little bit vain, this robot is making the whole idea of NASA's Regolith Mechanics Award looking a little mundane.
Yeah.
The rewards for somebody who comes up with a very unique way of handling regolith that becomes effective. But this old school method right here is working so well with good driver training. Oh, now he's got the rock. Oh boy. Keep the scoop down. Get up there. Lost it. Oh, he's got to push it now. Yeah, there you go. Push it, push it, push it, push it. Just roll it up. There we go. Oh, yeah. King of the mountain right there. My meatball on top of the spaghetti. This is crazy. Dare I say, this is lunacy?
That was a good one. That was a good one.
All right, stay away from my wall. Do you ever have that feeling when your driver is a little too confident in your machine?
Yeah, just sometimes.
I think we should have an award for a driver who has demonstrated the highest level of insanity. Because this driver is crazy. I'm gonna text somebody right now.
Uh-huh. I believe they're gonna try autonomy. Maybe.
I don't know. It's just my experience here, but I think if you're going to try autonomy at this point, it's kind of
Yeah.
insane. I mean, don't you expect a level terrain to do autonomy? There's nothing level about what's left in my arena.
Yeah.
Wow. In all the years I've been doing this, I have never seen this amount of material moved. And our robot moved a lot of material last year, but nothing like this. Nothing like this. Well, that might have been the autonomous one right there, because all you had to do was dump a little bit.
Yeah.
Yeah. Yeah, ideally it has to be in the thing, but the problem is getting to it now at this point. I mean, you have created a absolutely unnatural barrier. I don't know how we're going to score this one. I know this is a bit of exaggeration, but keep going at this rate, there'll be no distance left between the LiDAR and the top of the mound.
His goal when we first got here was to dig to the bottom of your pit, but guys, it's getting pretty close.
He's getting pretty close. Getting pretty close. I can tell the crew in the box is already hating him. That's a good thing. They'll probably just sit there and tell Jacob to keep the driving team in the mission control room and tell them they got to put it all back after scoring. Here we go again. If he's wanting to get points for acrobatic or drifting, I mean, he's doing a good job here. Yeah. I texted Eric Reiners just a little bit ago. That's the cat guy that he needed to see this run. I love the thing. You just do this little bit of toss.
Yeah.
Yeah. Okay, I'm gonna take a picture of this. This is. Get up here, you just stay right there.
Okay.
I think when he gets done with that, we'll carve Mount Rushmore on the side of it. Well, this is a very impressive run. We got 2.5 minutes left, and he's still putting. He's successfully built a ramp to the top of the berm. I think if the folks down at Florida at NASA would take a look at this right now, I think their heads would explode.
Yeah.
I am duly impressed by this run. Very duly impressed. This is wonderful. This is what we want to see. I really, really do. Now he's pushing the material that's outside of the area into the area. It's good machine control. But I think you're right. I think he's still going for the bottom of our pit.
Yeah.
It's a matter of pride now, right? Do you think you guys can hang around till Tuesday? I got a feeling facilities will want to ask him to empty our pit out for us.
I think he's dancing right now.
Tell him to stay away from my wall. That is wonderful maneuverability. He's going to try to pick on that rock. Yep. It's got 40 seconds left to pick on that rock. Maybe. He's thinking twice about that. What's he doing?
It looks like he's dancing.
Dancing. Question is what is he dancing to? Yeah, the only little tune is his head. Maybe we can get him to do the Macarena before he's done. My goodness gracious. Well, there we go. Wow. I think that is one of the finest runs in the history of Lunabotics mining. That is historical. Absolutely historical. And a lot of fun to watch. Wow. I can't wait to see the score on this one. Take a picture right off that computer screen. No, that's fine. You guys do whatever you want. Bring them over here if you want. All right. Well, Skylar, what's your impressions here?
Well,
I'm dumbfounded.
Yeah. Me too. It's good to see a robot finally work.
314 liters.
It's a lot.
Wow. I'm going to text this to Eric Reiners. That is a third of a cubic meter.
It's a lot.
You know, there's a great old commercial that Shukai Chevrolet in, and I'm not sure if I'm allowed to say this, but I'm going to say it anyway. Because I'm not supposed to say commercial phrases, but they're not a sponsor of ours. But there was an old commercial for Shukai Chevrolet. Guy said, "Come on, help me load it." And he said, "I ain't going to load it. Why not? Because I'm not going to be a part of hauling 2 tons of fertilizer in a 1-ton truck." I think that's 2 tons of fertilizer right there. So if we look at that, if that's what I think it is, that's 314 liters. Just sent that a second time to Eric. He's gonna choke on that. 314 times a probable density of 1.5 kilograms per liter. You're looking at 471 kilograms of material.
Hey,
That is a record.
it's a lot.
That is a record. Congratulations.
Oh, thank you. Yeah, thank you for giving us the opportunity to build something like this.
Oh, absolutely. It's been our pleasure. And it's exciting to see things happen here on something like that. This is just a double wow, all capital letters. All right.
I don't know if you want to talk to our driver, but here he comes.
Hey, crazy man. Crazy man, get over here.
Thank you again.
Yes, thank you, Skylar. Okay, I've got New Mexico Tech's driver coming over here. I got to find out exactly what makes this man as crazy as he is.
Hey, nice to meet you.
You have just accomplished a record in Lunabotics mining history. All the years that I've been involved, I have not known anybody The previous record was 273 kilograms.
Really?
Collected by Laurentian University out of Canada way back in 2011, 271 kilograms in 15 minutes. And in 30 minutes, you just collected 471 kilograms of material and dumped it in a pile that I don't know if I'm ever going to find that rock back. So I understand you had a little bit of training with skid steers already.
Yep. I mean, I grew up around construction equipment, so I can drive a lot of stuff. Grew up driving tractors, but I also spent, probably I spent 12 hours that I counted driving this exact robot in our test arena at Tech.
Now, let that be a lesson to all the other teams that are listening. Driver training, time spent on the machine, getting to know it and understanding your time of flight really makes a huge difference on the success of your competitive run. And this has been a very impressive run.
Thank you.
Just wow. And I know there's two guys in there right now that are using your name in vain in the arena as they're trying to get all this material put back and thinking that we're going to wind up being here till midnight just to get the next run ready to go, thanks to you.
Well, you're welcome for that. But I gotta say, it wouldn't have been possible without our team. I mean, these guys put in 4,500 hours over the past year.
That's what I
getting
understand.
this robot ready and getting it working. And without that, we would not have been nearly as successful as we were today.
Well, I have to say, it very impressive machine. I mean, it's a very basic, there's nothing novel here, but the execution in both driver training, reliable, durable systems, and such just really sometimes proves out that, you don't have to reinvent the wheel just to have something very successful. And it's very obvious here. Look at that person break a sweat. He's shoveling like mad. Wants to get ready for the next team, and you just created a whole lot of work for him. I don't think that area is ever going to be the same on there. I don't think we're going to find our way back to level ground.
Well, I was
There's
kind
so
of
much
hoping
there.
we dig down to the floor. They said that wasn't
That's what told me
possible.
there's a goal. Well, you came damn close. We were watching you a few times. I was about ready to call the Ames police and get you arrested for DUI while you were driving that robot, but I think you knew exactly what you were doing. That was very impressive, even on two wheels.
Yeah, we tipped over a couple times. I just sent it.
Yeah. But I have to say too, the durability of your motors, your drivetrain to hang on under those conditions of having up on two wheels without stripping out a drive or burning up a motor.
Oh, they were worried about that.
Oh,
They're
they should
really
be,
worried the weld was
especially with-
cracking and everything.
especially with you at the wheels. But no, that again, kudos on a very good design, very well built, very well operated. Wow. I could sit here and talk about it all night, and I'm going to be talking about this for a long, long time. And now our team's going to be going back and rethinking everything they thought they knew about lunabotics, thanks to you. Yeah, so excellent. Well, thank you so much.
Yeah, thank you. We're really
Congratulations
glad
on
to
an
be here.
excellent run. And we look forward to seeing the rest of the runs and seeing what the results of this competition are going to be and comparing it to the results from the NASA competition down in Florida. I think we just broke some new ground, pun intended. Thank you.
Yeah, thank you.
Okay. Excellent. So there we go, New Mexico Tech, the minor 49ers making a big name for themselves with an absolutely incredible run in our lunar arena, putting anything else we've ever done in the past to shame with collecting material. And now my team there in the box has got their work cut out for them to get this thing restored back to original condition, which I don't think will be an impossibility, but I think we're going to be here a while waiting for them to get that ready before we're ready for the next run. So glad you joined us. I hope you got a chance to catch this whole run. It was absolutely incredible. Just an excellent demonstration of driver training and robot construction and balance, and a little bit of art as well, and driving this thing and being successful on putting together a good run. I keep looking back here at the computer screen to watch my guys there. They're really huffing and puffing as they're trying to get this pit back together. And now we'll have to get, we got a fun little guest rolling in here. Our club has brought Wally along to run around in this area. And next, we're going to have Youngstown State University, the Penguin Moon Miners, coming in to run their little robot. It could very easily be a friend of Wally's. He's just as cute. But here comes Wally. I'm going to take a second here. I'm going to grab my mic and move it to the other side of the table. Just keep him right there. Because we move the camera? Yeah, that's what we're going to do. So I'm going to move the camera here a second so people online can see a little celebrity dance we have there. Pick it up. Yeah, here we have it. So we've got Wally. He's a little out of focus. I don't know if, is it something I did or is it something you can do? He's working on it. Let me see. Oh, got him out of camera. Sorry, folks. It's okay. There we go. So, club members work on this. This is a replica of Wally from the Pixar movie. He is going to be our ambassador for Cardinal Space Mining. Yeah. For STEM outreach to grade schools and junior high, because everybody loves Wally. And yes, that's right. And so we're going to be utilizing him to go to schools and show them what robotics is all about. Yeah, and so it'll be a lot of fun. So, yeah, nice little pirouette. He's made out of non-standard materials. There's a lot of 3D printed parts in here. The body is actually out of cardboard and paper stock, if you can believe that. His power is 2 Ryobi 20-volt drill batteries and various different motors and servos that drive him. His central computer is an Arduino, and he's run by an Xbox controller. And yeah, John has there. Okay, we got a servo start. Snap it. Can you stop that? Left arm. Yeah, see, there's a drive port. So we'll have to probably go in there and put a stop instead of port. So, no, you don't want that, Wally? You want me to leave your arm alone? Oh, okay. Well, I'm glad we have you here looking around. Are you going to go over and visit the teams in the pits? Great. Well, oh, very good. Very good. All right. Well, thank you for being here with us. Are we going to get to see you run in our lunar arena later? No? No? Are you just too advanced to do that? I thought so. Well, yeah, well, you need to go see Iris. She's waiting over there for you, but I'm sure that, yeah, that is University of Illinois robot. She's kind of your type. She's got tracks. Okay. Well, thanks for coming by, Wally. We'll see you later. Where do you want to right. So we'll get the camera back here where I think it should be. Okay. Okay, thank you. Yeah, right. About right here. Yeah. Okay. Actually. Virginia Tech tomorrow. So as soon as they get the robot in, they're in tech right now. We see their ground control crew in the mission control. No. Penguin Moon Miner can do its job and get a good run and get material into the deposit area. I mean, the weight and the size of this robot and the way they've run actually scored pretty well. After the first runs, they were in third place. If they can do a really good job in this run, depending on how the other teams do, they can still find themselves in a trophy position, even though it's small, but it's efficient. And this is fun to see as well. I won't see any craziness like we did in the last run, but that's okay. This is moon mining, and sometimes slow and steady is really the name of the game because it's all about energy efficiency. And we'll see how little Penguin Moon Miner does here. So let's watch and root for Youngstown State. Again, one of our rookie teams, along with Northeastern University out of Boston, is another rookie team that we have here. First time participating in lunabotics mining. So very, very happy to have them here. Very happy to be able to do this sort of event, that they're able to do these sort of things. Looks like our Penguin Moon Miner is being very tidy, staying right within the lines. That's good. Creating fairly smooth little area for him to mine. That's important. One of your big challenges, we saw this with the last run, you getting your terrain too uneven, and it gets to be a challenge unless you're a really insane driver like the last guy. To get your material in. So it's good to be thinking about your surface preparation as you're mining so that you can better control what it is that you're wanting to scoop up and get deposited. As you slip with your wheels and create ruts and divots, then that makes it a challenge for getting your scoop level maintained. They seem to be doing a pretty good job here, though. He's got another nice load coming in here. And getting a good dump position here. Filling up the back side of the berm area first, which is a good strategy. Okay, looks like I can get another good bite of material, picking it up, bringing it home. This is sortie 4. Averaging a little under 1 sortie a minute. Get a little more efficiency, get that sortie up as a sortie a minute, and you can get 30 sorties in there, maybe get a serious amount of material deposited. It's all about time and distance in doing this, and swept area as you're mining. How deep, how wide are you going? And how much energy does it take to do it? Because we do track the amount of energy these robots use. And that's part of the penalty points. The more energy you use, the more penalty points you get. And that becomes an issue. Oh, we're stuck on something a little bit. There he goes. And okay. That's sortie number 5. 6 minutes in. Getting the scoop down, ready to take another pass on the lunar regolith. See how the scoop bobbles up and down in here because of the surface conditions. Your wheels create a rut, and you think you got your scoop where you need it, and next thing you know, you're up above. But looks like they got a good bite there. Bringing it in. Taking it back to the berm. I really like the way they're being efficient with working their way across the berm area and depositing material. That previous run was very impressive as to the amount of material that they had, but it's not just material, it's energy, it's weight, it's dust mitigation, it's communication, it's autonomy points, autonomous operation that you do, and those all play part together in getting the score in order to win this competition. So even though brute force is always fun to watch, like we just saw in the previous run, sometimes slow and steady and efficient can take the day as well. So we'll see what they can do here. Again, this is a rookie team. This is their first time doing it. This is their first robot design. They used very elemental components for building the robot. Nothing too fancy here. And nothing too large, but very effective. You can see the camera that they have there, so they're able to see their load. And I would imagine they have some other cameras on there so they know where they're going with their robot. The wheel design was done very nicely, very light, very simple, but with good traction. I like the grab handles they have on the top of the robot too to pick it up. There's very good ergonomic design on the robot for handling. And that was one of the things that NASA had written in the rules, is to have feature on your robot for handling it. Very nicely done design. Team was telling me their first time through they were kind of disappointed they couldn't do machining that. I mentioned to them that's not necessarily to build a good robot. Knowing what you have available to you, making efficient use of those resources that you have, and designing a system that does the full mission as you plan to do it, that is a sign of a good design. And that's definitely what Youngstown State has here. So I'm looking forward to seeing them in the years of the future here, what they come up with for robotics designs, because this is a nice one. I've already lost count of the number of sorties, but by an estimate, I'm going to say this is probably sortie number 8. Getting to dump here. It's obviously this driver is not going to try to dig down to the bottom of arena like the previous one, and we appreciate that. That was a lot of work to get this pit put back together after that run, and my hat's off to our crew in the box for getting it done. Another nice little stab of material, and off to the berm area we go. Looks like he's going to go to the, whoops, keeping in the boundary there. Oh, nicely placed, nicely placed. Right in the corner. You're welcome. Okay, so here we go. Looks like we're on sortie number maybe 11 for Youngstown State. And their Penguin moon miner. Very nicely done. This little robot's cute to watch. He makes it look very routine, very mundane, no excitement, not like the last guy, who I still question his sanity on driving, but hey, he was successful. And I mean, to take a four-wheel robot and get it up on two wheels and not roll it over, that's pretty crazy. But we're not going to see anything like that out of Youngstown State. At least I hope not. They're more the tortoise than the hare, and this is the tortoise. Slow and steady sometimes wins the game. Light, compact, energy efficient. As long as they can maintain doing an efficient job of picking up material and getting it put in place and doing no hoopla, just getting it in there and keep building the berm, they just might be able to take the day with what they're doing. So again, it's all about time and distance, swept area. If you can minimize how far you got to go to collect material, if you can keep your working conditions in stable order. Right now he's getting some pretty significant wheel ruts there where he's sitting that can create issues with mining. So in that case, sometimes taking a moment to fill holes in, so in your next time back you're not having to deal with those uneven terrain issues, would help significantly on the run. But they're the ones driving, not me. And I'm just happy to be here watching and seeing these wonderful teams execute on their designs and seeing all this ingenuity and craftsmanship in putting these systems together and having them run. And this little robot, kudos to Youngstown. Oh, there's a good bite. Really has had no communications issues with the robot. It's been very good running. Their biggest issue has been and it looks like they've solved that issue, was the servo size for the bucket tip, and so that it runs regularly. Oh, there's a good dump. So now he's going to come back and get more material. Just watch out for that rock. Nicely done. Nicely done. Now we're going to take another line of action. It's got the scoop down, taking a pass, picking up the high points, getting a good amount of material without overloading the servos. Looks like he's got a good bite. Now just get it in there. I understand the temptation by some teams to go in and to get a little bit more, but sometimes in the sake of time, you're probably better off just taking what you have and getting it deposited and then coming back and getting more. Not only saying that for Youngstown's benefit, but I'm saying that for the benefit of my own team. Yeah. Because again, it's about time, distance, efficiency, swept area. Those are all the secrets in construction and mining and moving material. Whether you're collecting it for processing to get water or to get oxygen, oxides, or whether you're going to build a construction site, build a berm, build a building with overfill protection, which is one of the designs that NASA has for habitats. They would do a pre-designed inflatable habitat, put it on the surface of the moon, and then overfill it with regolith, and then put supports on the inside to hold the weight of the regolith. And that regolith would serve as a safety barrier for the micrometeorites that come in and bombard the planet. But you still have the issue of some fairly sizable meteorites that come in, and they're not going to burn up. And if they hit a habitat, they can destroy it. So actually, one of the things that NASA is looking at is is a geographic or a geological feature on the moon that you can find here on the Earth too. They're very prevalent on the island of Hawaii. It's called a lava tube. And lava flows will flow and empty an area subterranean wise, and then that actually becomes a geological feature you can use. It's kind of like a cave that's been made by the lava flow, just like a canyon can be made by a river carving through the earth. Well, they've found a few lava tubes on the moon. One of them is almost large enough to put a whole city inside of. It's huge, and it would serve as an excellent area to put a moon base in, and it would solve two immediate purposes that would be very well for having habitat on the moon. And the first one, actually I should say three. The first one is protection from radiation, because it's subterranean. All the radiation that's coming from the solar wind that would be bombarding you and creating problems for astronauts living long-term on the moon, they would be protected from that. Second of all, with the high degree of cover, it would be protecting you from all but the very largest asteroids that might hit the moon. And the moon still does get actively hit by micrometeoroids and meteoroids, and we just don't see any big asteroids hitting it. But there have been some flashes of light on the moon where something has hit, and we later see a fresh crater on the surface of the moon, particularly on the backside. And then lastly, and this is also kind of significant, being subterranean, the heat that gets generated on the solar surface from the lunar day stays trapped in the rock material, so that the temperature subterranean on the moon can be regulated at a more nominal 60 or 50 degrees Fahrenheit during a lunar night, because you have all of this internal heat stored into the rock of the moon. Whereas on the surface of the moon during a lunar night, the temperatures are getting down to a minus 173 degrees Fahrenheit. Quite cold, quite significant, and very hard to operate in. So these are things that to consider with what we're doing here with what we're doing on the moon. So what little penguin moon miner is doing here is doing a good job of building a berm. They're 2/3 of the way through their run. They're getting a nice pile built up, very neat and tidy. Love the way this little robot drives. Nothing flashy about it, just very efficient, doing its job, and doing it with very little power too at the same time. So not as exciting as the last one, but just as lovely with what they're doing with this robot. I have no doubt they'll go back and do some changes to the robot, make a few tweaks here and there, maybe add just a little more mass back into it. It's a very light robot. Maybe put a little more travel and a little more power on the actuators of the bucket. But as far as traction power, what they have there, they could get a little bit more with little taller grousers on their wheels, but I wouldn't want to get too much taller than what they have. The width of the bucket seems to do well. It's just here again too, speed of actuation by the bucket itself. It could be a little faster, a little more active. They could really do some good work with it. And if the servo is a little stronger so that the bucket doesn't get pulled under when it hits the material like it's doing there now, it has to back up a little bit in order to get the servos to pull the bucket up. It can't power through the material like the other robot did. And but nonetheless, doing a nice job. It kind of looks like maybe they're having some issues with their bucket, that maybe they overstressed it and it's not coming back to home position. Maybe the servos are burnt out. Their lift mechanism, I see they're actuating that, but the bucket's not responding to that. We'll see what they can do. A little bit of inventive driver maneuvering might still accomplish something for them. Maybe get a little closer to the berm area and see what they can do there with moving material. Durability is a big issue in these, a lot of times in these competitions. You got to start out something, but here again too, as you operate these motors, they can get quite hot if you push them too hard, and you push them hard enough, long enough, and the insulation melts, and then your motor's dead. And we see this happen a lot on these robots in the competition. The other big risk is getting stuck or shearing something by too much force. That's very common failure too on some of these systems. But regardless, Youngstown State has a nice run here. They got a fair amount of material into the berm area that they've deposited. They're still running and still maneuvering, so with a little bit of luck, maybe they can get things back. They seem to have gotten the bucket pulled back up into an optimal position, but now they're trying to position themselves into an optimal run. We'll see what's happening here. They can get backed up a little bit more to get another start into that. Okay, well, keep an eye on this and see how it goes. Okay, so we got about 6 minutes left. We'll stop moving. They're having a discussion with Jacob there, the judge, in the control area. We got some motion back. We're trying to push some material into the berm area. minutes, 40 seconds left. Look at the prior run. The New Mexico Tech points on their second run was 1,026. Their material collected was 309.9 liters. Which amounts to about 465 kilograms of material moved. Which I thought probably was a new record, but unfortunately it came up short. Laurentian University in 2011 moved 273 kilograms of material in 15 minutes. The equivalent here is 232 kilograms in 15 minutes. Still a very impressive run. I think this is a close second to anything that anybody has done in space mining, and they're to be applauded for that. Hey, good last run. Nice job, guys. Get a last bit of material pushed in there. Very well done. Nice run, Youngstown State. That'll be our last run for tonight. They'll go ahead and get their robot cleaned up. We'll get the regolith amount scored and get the points scored on that, and we'll see how they do on run 2. We will be back tomorrow morning, bright and early, with the second run for Virginia Tech Astrobotics. You've been watching the Collegiate Space Mining Competition, hosted by the Cardinal Space Mining Club, coming to you from the Student Innovation Center on the campus of Iowa State University in Ames, Iowa. Thank you for watching, and we will see you tomorrow.